Hello there, and welcome to Science for Sleep, where curiosity slows down just enough to let your mind wander without needing to arrive anywhere in a hurry. Tonight, we're stepping into a question that seems simple at first, almost too simple to notice, and yet it quietly sits underneath nearly everything we experience. It's about the present moment, not the past, not the future, just now. At first glance, that might feel like the most obvious thing in the world. Of course there is a now. You're in it. You're listening to this. Your surroundings are real. Your thoughts are happening. Your body is here, wherever here happens to be. It feels immediate, solid, and shared. Almost like the entire universe is paused together in this one thin slice of time. All of us aligned within the same cosmic moment. But before we go any further, I want to ask you something gently, the same way you might ask a quiet question late at night without expecting a quick answer. Where are you listening from right now, and what time is it in your part of the world? It's a small question, but it's surprisingly relevant, because even though we're all here together in this conversation, we're not actually sharing the same clock. Some of you might be deep into the night, others somewhere in the afternoon, and a few perhaps just starting your day. And if you find this kind of slow exploration calming, or even just a nice way to step away from the usual rush for a while, consider giving the video a like, or subscribing. It helps this quiet little corner reach others who might need a softer pace too. Now, let's ease into the idea. It's very natural to imagine that the universe has a single shared present moment, a kind of invisible now that stretches everywhere at once, like a perfectly flat surface slicing through reality. Everything that exists, every star, every planet, every person would be sitting on that same slice, experiencing the same instant together. If something happens here, we assume there must be a corresponding now somewhere else, even if we can't see it. This assumption is so deeply built into how we think that it rarely gets questioned. When you look at the night sky, for example, it's easy to imagine that what you're seeing is happening right now, somewhere out there. That distant star, that faint glow, it feels present, as if the universe is unfolding all at once in a shared moment. But physics, especially modern physics, has a habit of taking very familiar ideas and quietly turning them inside out. The first hint that something might be off comes from a simple observation about light. Light doesn't travel infinitely fast. It moves at a very specific speed, incredibly fast by everyday standards, but still limited. About 300,000 kilometers per second. That sounds instantaneous, but over large distances it begins to matter. If you look at the sun, you're not seeing it as it is right now. You're seeing it as it was about 8 minutes ago, because that's how long the light took to reach you. If the sun were to suddenly vanish, hypothetically, you wouldn't know for those 8 minutes. Your now would still include a sun that no longer exists in its own frame of time. Stretch that idea further, and it becomes even more striking. Some of the stars you see in the night sky are so far away that their light has taken hundreds or thousands of years to arrive. You're not seeing them in the present at all. You're seeing them as they were when civilizations on Earth were very different, or perhaps before they existed at all. So already something subtle begins to shift. The idea of a shared now starts to blur. The universe is not presenting itself all at once. It's delivering information with delays, layered across different times depending on distance. But that's only the beginning. The real turning point comes when we look at how motion affects time itself. This is where the work of Albert Einstein begins to quietly dismantle the idea of a universal present. In everyday life, we assume that if two events happen at the same time, they are simply simultaneous. If two lights flash in different places, and we say they happened at the same moment, that feels like a clear and objective statement. But according to special relativity, simultaneity is not absolute. It depends on how you are moving. Imagine two observers. One is standing still on a platform. The other is moving very quickly past that platform. Now imagine two lightning bolts striking at opposite ends of a train track. To the observer standing still, the flashes might appear at exactly the same time, but to the observer moving along the track, one flash will reach them slightly before the other. At first, this might seem like just a delay in perception, but relativity goes further. It says that both observers are correct in their own frame of reference. For one, the events were simultaneous. For the other, they were not. That means there is no single, objective answer to the question: did these events happen at the same time? The answer depends on who is asking and how they are moving. And if simultaneity depends on the observer, then the idea of a universal now begins to lose its footing, because now is essentially built from the idea of simultaneity. It's the collection of all events happening at the same time. But if different observers disagree on what counts as the same time, then they also disagree on what counts as now. So instead of one shared present moment, physics gives us something more personal. Each observer carries their own version of time, their own way of slicing the universe into past, present, and future. These slices don't line up perfectly between different observers. They tilt, shift, and overlap in ways that depend on motion and perspective. It's a bit like taking a loaf of bread and slicing it at different angles. Each slice is valid, each one cuts through the same loaf, but they don't all line up into the same flat layer. Once you start to see it this way, the universe becomes less like a synchronized clock and more like a collection of individual timelines, each one consistent on its own, but not globally aligned. This leads us toward a deeper idea, one that can feel slightly unsettling at first. If there is no universal present, then the distinction between past, present, and future may not be as fundamental as we thought. In physics, especially when we describe spacetime mathematically, time is treated as another dimension, alongside the three dimensions of space. Events are located not just by where they happen, but also by when. And all of these events, across what we would call past and future, exist within the same structure. This picture is often called the block universe. In it, the entire history of the universe is laid out as a four-dimensional structure. Nothing is coming into existence moment by moment. Instead, all events are simply there, located at different points in space-time. From this perspective, the feeling of a moving now is not something built into the universe itself. It's something that emerges from how we experience it. That might sound abstract, but you can think of it in a more grounded way. When you read a book, the entire story exists at once, printed on the pages. The beginning, middle, and end are all there. But as you read, you experience it sequentially, one moment at a time. Your sense of now moves through the story, even though the story itself is static. In a similar way, some interpretations of physics suggest that what we call the present moment is more about our experience moving through events, rather than something the universe is actively updating. But before we go too far into that idea, it's worth pausing here and noticing something important. Even if physics suggests that there is no universal now, we still feel one very strongly. You're experiencing this moment as present. Your thoughts, your awareness, your surroundings, they all feel anchored in a single point in time, so the question quietly shifts. Instead of asking only, does a universal now exist in the universe, we begin to ask, why does it feel like it does? Something interesting begins to happen when you stop and examine the way you naturally think about time during an ordinary day. Not in a scientific sense, not with equations or experiments, but in the quiet, automatic way your mind organizes reality without asking for permission. You wake up, perhaps check the time, maybe glance at your phone, and without needing to think about it, you assume that whatever moment you're in is shared by everything else. The world outside your window, the people in other cities, the planes crossing the sky, even the distant stars, all seem to exist together in the same present moment. It feels as though the universe is synchronized, like a vast system running on a single, invisible clock. That assumption is so smooth, so effortless, that it rarely draws attention to itself. It just sits there in the background, quietly shaping how you interpret everything. When you imagine someone far away, you picture them living their life right now. When you think about events happening elsewhere, you place them into your present as if time stretches out evenly across space, connecting everything into one shared slice of reality. And yet, that sense of a universal present is not something you ever directly observe. You never actually experience another place's now. You only ever experience your own. Still, the mind fills in the gaps. If a friend sends you a message, you imagine them typing it in their own present moment. If you watch a live broadcast, you assume what you're seeing is happening at the same time, even though there are always small delays, signals travelling, systems processing, information moving from one place to another. None of that usually matters to your intuition. The experience feels immediate, and so your brain labels it as now. This is where the illusion begins to take shape, not as a mistake, but as a useful shortcut. The human brain is not designed to track absolute physical truth in every detail. It is designed to build a stable and coherent version of reality that allows you to function, make decisions, and move through the world without hesitation. A shared present is part of that construction. It simplifies everything. Instead of constantly calculating delays, distances, and perspectives, your mind creates a unified stage where everything appears to unfold together. You can see this clearly in something as simple as a conversation. Imagine you're speaking with someone in front of you. You hear their words, you respond, they reply again. It feels continuous, immediate, and synchronized. But even here, there are tiny delays. Sound takes time to travel. Your brain takes time to process it. Your response takes time to form and be spoken. All of this is happening with slight offsets, but your perception smooths it into a seamless exchange. Now extend that idea outward. Think about watching a sports game on television. It feels live. The players move, the crowd reacts, the commentators speak as if everything is unfolding in real time. But the signal has travelled through cameras, satellites, servers, and screens before reaching you. What you call now is already slightly behind the event itself, and still your mind accepts it as present. This tendency becomes even more pronounced when distance increases. When you look at the moon, you're seeing it as it was about a second ago. When you look at the sun, you are seeing it as it was minutes ago. When you look at distant stars, you are seeing them as they were years, centuries, or even millennia in the past. Yet it does not feel that way. The sky does not appear layered with different times. It appears unified, as though everything you see belongs to the same moment. Your perception quietly edits out the delays and presents a coherent picture. The result is a powerful, convincing sense that there is a single, shared now stretching across the universe. But this sense is built from limited information. You're always located at one point in space, receiving signals that arrive at different times depending on their origin. Your brain gathers those signals and assembles them into a single experience. It does not label each piece with its actual timestamp. It simply places them together and calls it the present. In that way, what you experience as now is not a direct slice of the universe. It is a reconstruction. This reconstruction is incredibly effective. It allows you to navigate your environment without needing to consider the finite speed of light or the complexity of signal delays. You can catch a ball, cross a street, hold a conversation, all without consciously thinking about the fact that every piece of information you use is slightly out of date. But effectiveness does not mean accuracy at the deepest level. If you were to slow everything down, to examine each component of your experience with perfect precision, you would find that there is no single moment that all parts of reality share simultaneously. There are only signals arriving, each with its own history, each representing an event that occurred at a different time, and yet your mind insists on treating them as one. This is where the everyday illusion becomes clear. It is not that you are wrong in a practical sense. The idea of a shared present works well enough for daily life. It keeps things simple. It keeps your experience stable. But when you begin to look at the universe through the lens of physics, that simplicity starts to unravel. The illusion is reinforced by language as well. We speak about time as if it were uniform and universal. We say things like, "What are you doing right now?" or "That's happening at the same time." These phrases assume a shared temporal reference, a common now that everyone can point to. Language does not naturally account for relativity or signal delay. It reflects human intuition, not fundamental physics. Even our clocks contribute to the illusion. Clocks are designed to agree with each other. We synchronize them, adjust them, coordinate them across cities and continents. This creates the impression that time is globally consistent. If two clocks show the same reading, it feels like they are marking the same moment. But that agreement is maintained through careful systems and corrections. It is not a natural feature of the universe. It is something we impose, something we maintain. Without that coordination, different observers would measure time differently depending on their motion and position. The neat alignment of clocks that we rely on is a kind of human-made harmony, not an underlying rule of reality. All of this builds toward a subtle but important shift in perspective. The now you experience is real in the sense that it is part of your perception. It is how your mind organizes incoming information. It gives structure to your awareness and allows you to act within the world. But it is not a universal layer that exists independently of observers. There is no evidence, in modern physics, of a single moment that stretches across the entire universe, connecting all events into one shared present. Instead, there are many different ways of slicing time, depending on how you move and where you are. That idea can feel slightly disorienting at first. It challenges something that seems almost too obvious to question, but it also opens the door to a deeper understanding of how reality is structured. Because once you let go of the assumption of a universal now, you begin to see time not as a single flowing river that carries everything together, but as something more flexible, more dependent on perspective. Long before anyone began questioning whether a universal now even exists, there was a time when the answer seemed so obvious that it hardly needed to be stated. The universe, it was assumed, ran on a single, steady clock. Not a physical clock you could wind or hang on a wall, but a kind of invisible timing system built into reality itself, ticking forward the same way everywhere, for everything, without exception. This idea was formalized most clearly by Isaac Newton, whose work in the 17th century shaped the way scientists understood time for hundreds of years. In Newton's view, time was absolute. It existed independently of anything happening within the universe. It did not depend on motion, location, or perspective. It simply flowed. If you imagine the universe as a vast stage, Newton's time was the steady rhythm behind it all, like a metronome that never speeds up, never slows down, and never misses a beat. Planets could move, objects could fall, forces could act, but time itself remained unaffected. It provided the backdrop against which all motion could be measured. What made this idea so powerful was how well it worked. If you drop an object from a height, you can calculate exactly how long it will take to hit the ground. If you launch a projectile, you can predict its trajectory. If you observe the motion of planets, you can describe their orbits with remarkable accuracy. All of these calculations rely on a shared notion of time. A second is a second, no matter where you are. A minute passes the same way on Earth as it would anywhere else. That consistency made physics feel stable and predictable. In this framework, the idea of a universal present comes naturally. If time flows at the same rate everywhere, then at any given moment the entire universe can be described as existing in one shared state. There is a global now, a single slice of time that includes all events happening simultaneously. You could, in principle, imagine freezing the universe at a specific instant, like pausing a film and examining everything at once. every planet, every particle, every event would be part of that same moment. Then, as time moves forward, the universe advances together into the next instant, and the next, like frames in a perfectly synchronized sequence. This picture is simple, clean, and deeply intuitive. It matches how we naturally think about time in everyday life. When you check a clock and see that it is, say, 10 o'clock, you assume that it is also 10 o'clock everywhere else, adjusted only for human-made time zones. But underneath those adjustments, there is an implicit belief that there is a single underlying time that everyone is sharing. Newton's formulation made that belief explicit. He described time as something that flows equably without relation to anything external. In other words, time does not depend on events. It does not care whether anything is happening. It does not slow down or speed up. It simply continues steady and uniform. This leads to an important consequence. If time is absolute, then simultaneity is also absolute. Two events either happen at the same time, or they do not. There is no ambiguity. No observer can disagree about it. If two lightning bolts strike at the same moment, then that fact is true everywhere in the universe, regardless of who is observing or how they are moving. That assumption sits quietly underneath classical physics. It allows you to compare events across space without needing to account for differences in perspective. You can say that one event happened before another, or that two events happened at the same time, and those statements are universally valid. There is no need to ask, according to whom? Because in Newton's universe, the answer would always be the same. This is what gives rise to the idea of a shared cosmic clock. You can think of it as a master timeline that runs through the entire universe. Every event can be assigned a position on that timeline. Every observer, no matter where they are or how they move, agrees on the ordering of those events. The universe evolves in a single, coordinated way, moving from one moment to the next in perfect synchrony. For centuries, this picture held together remarkably well. It was not just a philosophical idea. It was supported by observation and experiment. The motions of objects on Earth, the behavior of projectiles, the orbits of planets, all followed the predictions of Newtonian mechanics with impressive accuracy. There was no obvious reason to doubt the underlying assumptions about time, and because those assumptions worked so well, they became deeply embedded in both science and everyday thinking. Even outside of physics, the idea of a universal present became part of how people understood the world. It shaped language, culture, and intuition. We speak of events happening at the same time, as if that phrase refers to something objective and unambiguous. We imagine history unfolding along a single timeline, with a clear distinction between past, present, and future. All of that fits naturally within Newton's framework. But there is something quietly hidden within this picture that only becomes visible when you start to push the limits of observation. Newton's time assumes that information can be compared instantly across space. If two events happen far apart, you can still say whether they occurred at the same time, because time itself is universal. But in practice, you never observe distant events directly. You only receive signals from them, and those signals take time to travel. In Newton's era, this limitation did not seem significant. The speeds involved in everyday life are so small, and the distance is relatively modest, that any delays in information are negligible. Light appears to travel instantaneously. Signals seem immediate. The assumption of a shared present feels justified. However, as measurements became more precise and experiments more refined, it became clear that light does not travel infinitely fast. It has a finite speed, and that speed is the same regardless of how you move. This discovery introduced a tension into the classical picture. If information cannot travel instantly, then determining whether two distant events happened at the same time becomes more complicated. You can no longer assume that you can compare them directly without accounting for the time it takes for signals to reach you. At first, this might seem like a practical limitation rather than a fundamental problem. Perhaps the universe still has a universal now, even if we cannot always observe it perfectly. But as we continue to follow this line of reasoning, something more profound begins to emerge. The assumption of a shared cosmic clock starts to depend on how we define simultaneity, and that definition, it turns out, is not as straightforward as it once seemed. Still, before that shift fully takes hold, it's worth appreciating just how compelling the classical view of time really is. It offers a universe that is orderly and predictable, a universe where cause and effect are clearly defined, where events unfold along a single timeline, and where the present moment is a real shared feature of reality. It gives us a stable foundation on which to build our understanding of motion, forces, and interactions. And even today, in many situations, this picture works perfectly well. When you throw a ball, drive a car, or track the motion of everyday objects, Newton's time provides an accurate description. You do not need to worry about relativity or the breakdown of simultaneity. The differences are too small to matter. So in a practical sense, the idea of a universal present still holds together in much of our daily experience. But as soon as we step beyond those familiar scales, as soon as we begin to consider higher speeds or larger distances, the cracks in that picture begin to widen. The shared cosmic clock, so reliable and intuitive, starts to lose its universality. There is a small step hidden inside classical physics that feels so natural you almost don't notice it happening. It sits quietly between the idea of time flowing and the idea of a shared present, linking the two together without much resistance. That step is the assumption of simultaneity. In simple terms, simultaneity means that two events happen at the same time. Not approximately, not from a particular point of view, but truly, objectively, and universally at the same moment. If one event occurs here and another occurs far away, the assumption says there is a definite answer to whether they are happening together or not. At first, that sounds almost too obvious to question. If two light bulbs turn on at the same instant, then they turn on at the same instant. If two clocks strike noon, then it is noon for both. The idea feels clean, straightforward, and reliable. It fits neatly into the picture of a universe governed by a single, steady timeline. But if you look a little closer, something subtle begins to emerge. The only way you ever decide whether two events are simultaneous is by observing them, or more precisely by receiving information about them, and that information does not arrive instantly. Imagine two distant events happening far apart in space. Perhaps two flashes of light, one on one side of a field and another on the opposite side. If you stand exactly in the middle, and the flashes reach you at the same moment, it feels reasonable to conclude that they happened at the same time. This is the intuitive definition of simultaneity. Equal arrival times imply equal occurrence times, but there is an assumption hiding inside that reasoning. You're assuming that the signals from both events travelled at the same speed, and that you are positioned in such a way that any delay is symmetric. If either of those conditions is not true, the conclusion becomes less certain. Now imagine you are not standing still. Suppose you are moving toward one of the flashes and away from the other. In that case, the light from the flash you are moving toward will reach you sooner, and the light from the other will take longer. If you simply compare arrival times, you might conclude that one event happened earlier than the other. You could try to correct for this by taking your motion into account, but now the situation becomes more complicated. You need a method for defining simultaneity that works regardless of where you are or how you are moving. In classical physics, this problem is solved by assuming that there is a universal time in the background. Even if your observations are delayed or distorted by motion, there is still a true answer about when the events occurred. Simultaneity exists independently of your perspective. Your job is simply to measure it correctly. This is where synchronized clocks come into play. To determine whether two distant events happen at the same time, you might place a clock at each location. If both clocks read the same time when their respective events occur, then the events are simultaneous. Simple enough. But now a new question appears. How do you ensure that those clocks are actually synchronized? If the clocks are in the same place, synchronization is easy. You can set them side by side. But if they are far apart, you need a way to coordinate them across distance, and that requires sending signals. One common method is to send a light signal from one clock to the other. You note the time the signal is sent, the time it is received, and you assume that the signal travelled at a constant speed. Using that assumption, you can adjust the clock so that they agree. At this point, something important happens. Your definition of simultaneity now depends on how you define the behaviour of light. You're assuming that light travels at the same speed in all directions, and that this speed can be used as a reliable reference for synchronization. In classical physics, this assumption seems reasonable and unproblematic. It allows you to establish a consistent network of clocks and define a shared timeline across space. Once the clocks are synchronized, you can compare events and determine whether they are simultaneous. But notice what has happened. Simultaneity is no longer something you directly observe. It is something you define through a procedure. It depends on how you synchronize clocks, which in turn depends on assumptions about how signals travel. This is the first sign that simultaneity might not be as absolute as it appears. If different observers use different methods, or if their assumptions about signal behavior differ, they might arrive at different conclusions about whether events are simultaneous. In classical physics, this possibility is usually dismissed because the underlying framework assumes a single, universal time that all observers share. However, once you begin to question that framework, the situation changes. Consider again the idea of a universal now. It relies entirely on the assumption that simultaneity is absolute. If all observers agree on what events are happening at the same time, then there is a single present moment that spans the universe. But if simultaneity becomes relative, if different observers can disagree about which events are simultaneous, then the concept of a shared present begins to fall apart. This is where the classical picture starts to reach its limits. The assumption of simultaneity works well, as long as you do not push it too far. In everyday situations where speeds are low and distances are manageable, any discrepancies are too small to notice. Clocks can be synchronized with high precision, and the idea of a shared now remains practical and useful. But as you move toward higher speeds and larger distances, the cracks begin to show. The finite speed of light, which seemed like a minor detail, becomes central. It forces you to confront the fact that all observations are delayed, that information takes time to travel, and that your view of distant events is always slightly out of date. More importantly, it raises a deeper question. If the only way to define simultaneity is through the exchange of signals, and if those signals are limited by the speed of light, then is there really a single observer-independent notion of at the same time? Or is simultaneity something that depends on how you're moving, how you measure, and how you interpret the signals you receive? Classical physics answers this question by holding on to the idea of absolute time. It assumes that, despite the practical challenges of measurement, there is a true underlying simultaneity that exists independently of observers. But that answer, while convenient, is not the only possibility. There is a point in the story of physics where everything still seems stable, predictable, and comfortably aligned with intuition, and then a single detail begins to behave differently than expected. Not dramatically at first, not in a way that immediately breaks the entire picture, but quietly, persistently, in a way that refuses to fit. That detail is light. For a long time, light was treated much like any other moving thing. If you throw a ball from a moving train, someone standing on the platform will measure its speed differently than someone on the train. The motion of the source adds to the motion of the object. This idea works so well in everyday life that it feels almost unavoidable. Speeds add together. That is how motion behaves. So it was natural to assume that light would follow the same rule. If a source of light is moving, then the light it emits should move faster in the direction of motion and slower in the opposite direction, at least relative to an outside observer. That expectation fits neatly into the classical picture of time and space. Everything moves within a fixed background, and speeds combine in predictable ways. But when scientists began to measure the speed of light with increasing precision, something unusual started to appear. No matter how they tried to detect a difference, no matter how the source was moving or how the observer was positioned, the speed of light remained the same. It did not add up with the motion of its source. It did not slow down or speed up depending on perspective. It behaved as though it had a fixed speed built into the fabric of reality itself. This result was confirmed most famously by the Michelson-Morley experiment in the late 19th century. The goal of that experiment was to detect the motion of Earth through a medium that was thought to carry light, something called the luminiferous ether. If Earth were moving through this medium, then the speed of light should vary depending on direction, much like the way the speed of sound depends on wind. But no such variation was found. Light arrived at the same speed in every direction, regardless of Earth's motion. It was as if the ether did not exist, and light did not need a medium to travel through. More importantly, it suggested that the speed of light was not behaving like ordinary speeds at all. At first, this result was puzzling rather than revolutionary. Scientists attempted to explain it within the existing framework, proposing adjustments and modifications to preserve the idea of absolute space and time. But the more carefully the problem was examined, the more difficult it became to maintain the classical assumptions. Then, in the early 20th century, Albert Einstein approached the situation from a different angle. Instead of trying to fit the behavior of light into the existing structure, he asked a more direct question. What if the speed of light really is the same for all observers, no matter how they move? And what if the laws of physics are the same in all inertial frames, meaning no observer has a preferred state of motion? If those two ideas are taken seriously, then something else has to give. And what gives, as it turns out, is the structure of time itself. Because if the speed of light is constant for all observers, then measurements of distance and time can no longer remain fixed and universal. They must adjust in such a way that the speed of light remains the same, regardless of motion. This is not an optional adjustment, it is a necessary consequence. To see why, imagine two observers. One is standing still, and the other is moving at a high speed. Both measure the speed of a beam of light passing by. According to the new understanding, both must obtain the same value. But if the moving observer is travelling toward the light, classical intuition would suggest that they should measure a higher speed, just as you would encounter raindrops more frequently if you run toward them. Yet that does not happen. Instead, something else changes. Time itself begins to behave differently for the moving observer. Their clocks tick more slowly relative to the stationary observer. Distances along the direction of motion also contract. These effects work together to ensure that the speed of light remains constant. At this point, the idea of a shared cosmic clock starts to unravel. If time can slow down or speed up depending on motion, then there is no longer a single, universal rate at which time flows. Each observer carries their own time, their own sequence of moments, which may not align perfectly with those of others. And once that happens, simultaneity begins to lose its absolute meaning. Events that appear to occur at the same time for one observer may not appear simultaneous for another who is moving differently. The constant speed of light forces this conclusion. It does not allow all observers to agree on the timing of distant events. This is where light changes everything. What once seemed like a small detail about how fast light travels turns out to be a fundamental constraint on the structure of reality. It reshapes our understanding of space and time, linking them together in ways that were not previously considered. Instead of having a separate space and a separate time, both fixed and universal, we begin to see them as part of a unified framework, where measurements depend on the observer. And within that framework, the idea of a single, shared now becomes difficult to maintain. Because if observers moving at different speeds disagree about the timing of events, then they also disagree about which events belong to the present moment. Each observer effectively carries their own version of now, defined by their motion and perspective. This does not mean that reality becomes chaotic or undefined. The laws of physics remain consistent. Each observer's measurements are internally coherent. What changes is the relationship between different observers. Instead of all perspectives aligning into a single timeline, they form a network of overlapping but distinct descriptions, each valid within its own frame of reference. Light in this sense acts as a kind of boundary. It sets a limit on how information can travel and how events can be compared. It ensures that no signal can move faster than it does, and that this speed remains the same for everyone, and by doing so, it forces time to become flexible. What began as an attempt to measure the speed of light more precisely ends up revealing that time is not the fixed background we once assumed. It bends, stretches and shifts depending on motion, all to preserve a single, unchanging constant. So the assumption that once seemed so secure, the idea that time flows uniformly everywhere, begins to give way. A young patent clerk sitting in a quiet office is not the usual image of someone about to reshape the structure of reality, and yet that is exactly where the next shift begins. No laboratory filled with complex machines, no towering observatory, just careful thinking, a few bold assumptions, and a willingness to question something that had gone largely unchallenged for centuries. When Albert Einstein started working through the implications of light's strange behaviour, he was not trying to make time more complicated. In fact, his goal was almost the opposite. He wanted to remove inconsistencies, to build a picture of physics where the rules stayed the same for everyone, regardless of how they moved. That idea, simple as it sounds, carried a hidden consequence. If the laws of physics are truly the same in all inertial frames, meaning in all frames moving at constant velocity, then no observer should be able to perform an experiment and determine whether they are really at rest or really in motion. Motion becomes relative, not absolute. That part had already been understood since the time of Galileo. But when this principle is combined with the constant speed of light, something deeper begins to shift. Because if everyone must measure the same speed of light, then the usual way of adding velocities cannot hold. Think about it carefully. In everyday life, if you walk forward on a moving train and toss a ball ahead of you, someone standing on the platform will measure the ball's speed as the speed of the train plus the speed of your throw. Speeds combine. That rule feels so obvious that it almost defines how we think about motion. But light refuses to follow that rule. No matter how fast you move toward a beam of light, you do not measure it as arriving faster. No matter how quickly you chase it, it does not slow down relative to you. It remains fixed at the same speed, always. To preserve that fact, something else must adjust. Einstein's insight was to accept this fully and then follow the consequences wherever they led. Instead of modifying the behavior of light, he allowed space and time themselves to change. This is the first disruption. Not a gradual adjustment, not a small correction, but a fundamental shift in how we understand the relationship between observers and reality. According to special relativity, measurements of time are not universal. They depend on the motion of the observer. A moving clock does not tick at the same rate as a stationary one, at least not from the perspective of another observer. The faster the relative motion, the more noticeable the difference becomes. This effect is called time dilation. It does not mean that time slows down in an absolute sense. Each observer experiences their own time normally. Their own clock ticks steadily. Their own processes unfold as expected. But when observers compare their measurements, they find discrepancies. One clock may have recorded less elapsed time than another, simply because it was moving differently. Already the idea of a shared cosmic clock begins to lose its foundation. If time itself depends on motion, then there is no single rate at which the universe evolves. There is no master timeline that everyone follows equally. Instead, there are many timelines, each tied to the motion of a particular observer. But the disruption goes further. To keep the speed of light constant, space must also adjust. Distances along the direction of the motion contract. Length itself becomes relative, changing depending on how you are moving. Time and space are no longer separate, fixed entities. They begin to behave as parts of a single system. This is where the familiar picture starts to break down. In classical physics, you could imagine events happening within a stable framework. Space provided the stage, time provided the rhythm, and everything else unfolded within that setting. Now, the stage and the rhythm are no longer fixed. They respond to motion, bending just enough to preserve a deeper consistency. That consistency is the invariance of the speed of light, and once that principle is accepted, it reshapes everything built on top of it. One of the most immediate consequences is the loss of absolute simultaneity. If two observers are moving relative to each other, and if their measurements of time differ, then their judgments about which events happen at the same time must also differ. Events that line up neatly into a single moment for one observer may not line up for another. This is not a limitation of measurement, it is a fundamental feature of how spacetime is structured. To make this more concrete, consider a simple scenario. An observer is at rest relative to a pair of events, perhaps two flashes of light occurring at equal distances on either side. For that observer, the flashes appear simultaneous. The light from both events reaches them at the same moment, and because they are equidistant, there is no reason to think otherwise. Now introduce a second observer, moving relative to the first. From this moving observer's perspective, the situation changes. They are moving toward one flash and away from the other. Even if the flashes were simultaneous in the first observer's frame, the moving observer will receive the light from one flash before the other. But here is the key point. Because the speed of light is the same for both observers, the moving observer cannot simply attribute the difference to their motion through the light. Instead, they must conclude that the events themselves were not simultaneous in their frame of reference. So now there are two valid descriptions. For one observer, the events happened at the same time, for the other, they did not. This is the moment where the classical idea of a universal now breaks. There is no longer a single answer to the question, which events are happening right now? The answer depends on your state of motion. Each observer has their own set of events that they consider simultaneous, their own version of the present moment. Einstein's first disruption, then, is not just about light or speed. It is about removing the assumption that time is shared equally by all observers. Instead, time becomes something personal, tied to motion, relative rather than absolute. And once that idea is accepted, the structure of reality begins to look different. Rather than a single timeline flowing uniformly across the universe, we begin to see a network of intersecting timelines, each corresponding to a different observer. These timelines do not always agree on the ordering of events. They do not always share the same now. What remains consistent is not time itself, but the laws that govern how time and space transform between observers. This shift is subtle in everyday life, because the speeds we encounter are so small compared to the speed of light. The differences in time and length are tiny, far too small to notice without precise instruments. For practical purposes, the classical picture still works, but at a fundamental level, the disruption is complete. Time is no longer a universal backdrop. It is part of a dynamic relationship between observers and the events they measure. Instead of beginning with motion or clocks, it helps to start with a simple expectation, the kind that feels so obvious it almost seems unnecessary to explain. If two things happen at the same time, then they happen at the same time. That statement sounds almost circular, as if it defines itself. And for a long time, that is exactly how it was treated. But once the implications of relativity begin to settle in, that certainty starts to loosen. The relativity of simultaneity is not a small correction or a technical detail tucked away in advanced physics. It is one of the central consequences of taking the constant speed of light seriously. It tells us that the question, did these events happen at the same time, does not have a single universal answer. Instead, the answer depends on the observer. That idea is easy to state, but it takes a moment to feel what it really means. Consider two events that occur at different locations. Perhaps two distant explosions or two lights switching on. In classical thinking, there is a fact of the matter about whether they are simultaneous. Observers might disagree due to delays in receiving information, but underneath those delays there is a true timing that everyone would agree on if they could measure perfectly. Relativity removes that underlying agreement. To see how this happens, imagine an observer positioned exactly midway between the two events. Light from both events travels toward them, and if the flashes arrive at the same moment, the observer concludes that the events were simultaneous. This conclusion is not arbitrary. It follows from a reasonable method of measurement, assuming that light travels at the same speed in both directions. Now introduce a second observer, moving steadily relative to the first. This moving observer is no longer centered between the two events in the same way. They are moving toward one location and away from the other. When the light from both events travels toward them, it still moves at the same speed, but the observer's motion changes when and where they meet those signals. They will encounter the light from one event before the other. At first, it might seem that this is just a difference in perception, something that could be corrected if the observer accounts for their motion. But here is where relativity becomes precise. Because the speed of light is the same for all observers, the moving observer cannot simply say that one signal caught up faster because they were moving toward it. Instead, they must conclude that the signals were emitted at different times in their frame of reference. In other words, for the moving observer, the two events were not simultaneous. Now there are two equally valid descriptions of the same pair of events. One observer says the events happened at the same time, another says one happened before the other. Neither is mistaken. Both are applying the same physical laws and both are measuring consistently within their own frames of reference. This is the relativity of simultaneity. It does not arise from faulty measurement or lack of information. It arises from the structure of space-time itself. The way time and space are linked ensures that different observers, moving relative to one another, will slice events into moments differently. You can think of it in a geometric way. Instead of imagining time as a universal sequence of flat layers, each representing a shared now, imagine that each observer carries their own set of layers. These layers tilt relative to one another depending on motion. What counts as simultaneous for one observer corresponds to a particular slice through space-time, while another observer's slice is angled differently. Both slices pass through the same overall structure, but they intersect different sets of events. That means each observer has their own version of the present. For one observer, a distant event might belong to their now. For another observer moving differently, that same event might lie in their past or their future. The classification is not absolute. It depends on the observer's state of motion. This idea can feel slightly disorienting because it challenges a deeply rooted intuition. We're used to thinking of the present as something objective, something that exists independently of perspective. The relativity of simultaneity replaces that with something more flexible. The present becomes a property of an observer's frame of reference, not a feature of the universe as a whole. Even more interestingly, this effect is not limited to extreme situations. It is always present, even at low speeds, but the differences are so small that they go unnoticed in everyday life. Only when velocities approach the speed of light do the discrepancies become large enough to measure directly. Still, the principle holds at all scales. Any two observers moving relative to each other will, in principle, disagree about the simultaneity of distant events. The disagreement may be tiny, but it is real. This has important consequences for how we think about time. If there is no universal simultaneity, then there is no universal present. There is no single set of events that everyone can agree are happening right now. Each observer has their own definition, their own slice of space-time that they consider to be the present moment. This does not mean that reality becomes inconsistent or contradictory. The laws of physics provide precise rules for translating between different observers' perspectives. If one observer measures two events as simultaneous, another observer can calculate exactly how those events are ordered in their own frame. The relationships are consistent, even if the interpretations differ. What changes is the idea of a shared temporal framework. Instead of a single timeline that everyone follows, we have a collection of timelines, each associated with a different observer. These timelines intersect and overlap, but they do not align into a single universal sequence of moments. At this point, the notion of a cosmic now has been significantly weakened. It is no longer supported by the structure of physical laws. Instead, it emerges as a useful approximation in situations where relative motion is negligible. In those cases, different observers' slices of simultaneity are nearly aligned, and the illusion of a shared present holds. But as soon as motion becomes significant, the illusion fades. The relativity of simultaneity reveals that time is not something that can be separated cleanly from the observer. It is part of the relationship between events and the paths observers take through space-time. Picture a long, straight stretch of track, the kind that seems to go on just a little farther than you expect when you look down it. There is a train moving along that track at a steady speed, not accelerating, not slowing down, just gliding forward smoothly. On the ground beside the track stands an observer watching the train pass by. Inside the train, exactly at its midpoint, sits another observer. Now imagine that at a particular instant, two bolts of lightning strike the track. One hits the front end of the train, and the other hits the back end. Both strikes leave bright flashes of light that spread outward in all directions. From the point of view of the observer standing on the ground, something very specific happens. The lightning bolts strike the front and the back at the same time. This observer is positioned exactly halfway between the two strike points. Light from both flashes travels toward them at the same speed, and both flashes arrive at the same moment. So based on a reasonable method of measurement, the ground observer concludes that the two lightning strikes were simultaneous. That conclusion fits perfectly within the classical idea of time. Equal distances, equal speeds of light, equal arrival times, therefore equal occurrence times. Everything lines up cleanly. Now shift your attention to the observer sitting inside the train. This observer is also positioned at the midpoint of the train itself. At the moment the lightning strikes, they are exactly halfway between the front and the back of the train. But unlike the observer on the ground, they are moving along the track together with the train. As the flashes of light spread out from the two strike points, the situation for the train observer begins to differ. Because the train is moving forward, the observer inside it is moving toward the point where the front lightning strike occurred, and away from the point where the back lightning strike occurred. The light from the front strike has a shorter distance to cover before reaching them, while the light from the back strike has a longer distance to travel. Both beams of light still move at the same speed. That part does not change, but the observer's motion changes when and where those beams meet them. As a result, the observer on the train sees the flash from the front first, followed by the flash from the back. At this stage, it might be tempting to say that the train observer is simply receiving the signals at different times, even though the events themselves happen simultaneously. That would be the classical explanation. You could argue that their motion caused the difference in arrival times, and that with proper corrections they could still conclude that the strikes were simultaneous. But this is where relativity steps in and changes the rules. Because the speed of light is the same for all observers, the train observer cannot explain the difference in arrival times by saying that one beam of light was effectively faster or effectively slower. Both beams travelled at the same speed relative to them, so the only consistent conclusion is this. From the train observer's perspective, the lightning strike at the front happened before the strike at the back. Now there are two observers, both applying the same physical laws, both reasoning carefully, and both reaching different conclusions about the timing of the same events. The ground observer says the strikes were simultaneous, the train observer says they were not, and neither is wrong. This thought experiment, first described by Albert Einstein, is not just a clever puzzle. It captures the essence of the relativity of simultaneity in a way that is concrete and difficult to dismiss. What makes it particularly powerful is that it does not rely on exotic conditions. There is no need for black holes, no need for extreme gravitational fields. It involves a train, a track, and 2 flashes of light. The only requirement is that the speed of light is constant for all observers. From that single requirement, the disagreement about simultaneity follows inevitably. You can think of it as a shift in how different observers slice the sequence of events. The observer on the ground draws a line through spacetime that connects the 2 lightning strikes into a single moment. For them, both events belong to the same now. The observer on the train draws a different line. Their version of now tilts relative to the ground observers. In their slice of reality, the front strike comes first and the back strike follows. Both slices are valid. Both pass through the same set of events, but they group those events into moments differently. This is where the idea of a universal present begins to collapse completely. If 2 observers can disagree about whether 2 events happened at the same time, then there is no single, observer, independent definition of now. The present moment is no longer a global feature of the universe. It becomes something defined locally, relative to each observer's motion. What feels like a shared moment in everyday life turns out to be an approximation. At low speeds, the differences between observers are so small that they can be ignored. The slices of simultaneity for different observers are nearly aligned, and the illusion of a universal now holds. But as speeds increase, the misalignment grows, and the differences become impossible to ignore. The train and lightning scenario makes this visible. It shows, step by step, how the assumption of simultaneity breaks down when you account for the finite speed of light and the relative motion of observers. It reveals that at the same time is not a simple, universal statement, but something that depends on perspective, and once that idea is accepted, it becomes clear that time cannot be separated from the observer. Each observer carries their own timeline, their own way of ordering events, their own version of the present. These timelines intersect, overlap, and can be translated into one another using the rules of relativity, but they do not merge into a single, shared sequence. What begins to emerge once you accept that different observers can disagree about simultaneity is that the old way of separating space and time into 2 independent things no longer holds together. You can't keep space fixed and let time vary, or keep time fixed and let space vary, because the 2 are now linked. Change one, and the other must adjust as well. This realization led to a shift that was just as important as Einstein's original insight, and it was expressed most clearly by the mathematician Hermann Minkowski. He proposed that space and time should not be treated as separate entities at all, but as parts of a single, unified structure. That structure is what we now call spacetime. At first, the idea might sound like a simple combination of words, as if someone just decided to glue space and time together for convenience. But it is more than that. It is a different way of describing reality, one that naturally incorporates the effects of relativity without needing to patch them in afterward. Instead of thinking of objects as existing in space and then evolving in time, you begin to think of everything as existing within space-time, where both position and time are coordinates that define events. An event in this context is something very specific. It is not just an object or a place. It is a point defined by where something happens and when it happens. For example, a flash of light occurring at a certain location at a certain time is an event. Every physical occurrence can be described this way. In classical thinking, you might list the position of an event using 3 coordinates, length, width, and height, and then attach a time separately. In space-time, all 4 of these are treated together as a single set of coordinates. So instead of saying, "This happened here at this time," you describe it as one point in a 4-dimensional structure. That shift changes how you picture the universe. Rather than imagining the universe as a sequence of 3-dimensional snapshots evolving through time, You can imagine it as a four-dimensional structure that already contains all events. Past, present, and future are not separate layers that come into existence one after another. They're all part of the same overall geometry. This does not mean that time disappears. It means that time is built into the structure, just like space. To get a more concrete sense of this, think about how you would describe your own location right now. You might say you're in a particular room, in a particular building, in a particular city. That gives your position in space. But if someone wanted to know exactly where you are in the context of the universe, they would also need to know when. Your location at one moment is not the same as your location a minute later, even if you do not move physically. The time coordinate distinguishes between those moments. Without it, the description is incomplete. Spacetime takes that idea seriously. Every object traces out a path through spacetime as it moves. Even if it appears to be at rest in space, it is still moving forward in time. That path is sometimes called a world line. It represents the sequence of events that make up the history of that object. In this picture, motion is not just movement through space, it is movement through space-time. This is where the earlier discussion about simultaneity becomes clearer. When different observers disagree about what events are simultaneous, what they are really doing is slicing space-time in different ways. Each observer defines a set of events that they considers to be happening at the same time, and that set forms a kind of slice through the four-dimensional structure. But these slices are not unique. One observer's slice can be tilted relative to another's. They intersect the same space-time, but they group events differently into moments. What counts as now for one observer corresponds to a particular slice, while another observer's now corresponds to a different slice. There is no single slice that is preferred by the laws of physics. This is a crucial point. In classical physics, there was an implicit assumption that one particular slicing of time was the correct one, the universal present that everyone shared. In space-time, that assumption disappears. All inertial observers are equally valid, and none of their definitions of simultaneity is singled out as the true one. So the idea of a universal now does not appear anywhere in the structure. Instead, what exists are events and the relationships between them. Some events can influence others, and some cannot. This is determined by the speed of light, which sets a limit on how quickly information can travel. If one event lies within the future light cone of another, then a signal travelling at or below the speed of light can connect them. If it lies outside, then no such connection is possible. This introduces a different way of organising events. Rather than dividing them into past, present and future based on a universal clock, space-time divides them based on causality. Events are classified by whether they can affect each other. Your past consists of events that could have influenced you. Your future consists of events you could influence. And then there are events that are neither. Events that are too far away in space-time for any signal travelling at the speed of light or slower to connect them to you. Those events do not have a well-defined temporal order relative to you. Different observers can disagree about whether they are in the past or the future, and there is no contradiction in that. This is another way in which the idea of a shared now fades. For distant events that cannot influence each other, there is no absolute answer to the question of which one is happening right now. Their ordering depends entirely on the observer's frame of reference. Space-time replaces the notion of a universal present with a structure that respects the limits of causality and the relativity of motion. It provides a framework in which all observers can describe events consistently, even if they do not agree on their timing. And perhaps most importantly, it shows that time is not something that flows independently of space. It is intertwined with it, forming a single system that determines how events are related. Once you begin to see the universe this way, the earlier ideas start to fall into place. The disagreement about simultaneity is not a flaw or a paradox. It is a natural consequence of how space-time is organised. Different observers are simply choosing different ways to slice the same four-dimensional structure, and because there is no preferred slicing, there is no preferred present. What remains is a richer, more flexible picture, one where the concept of now is not built into the universe itself, but emerges from how observers move through space-time and how they choose to define their coordinates within it. Another way to approach this shift is to stop thinking about moments altogether, at least for a moment, and instead focus on continuity. Not snapshots, not slices of now, but the full, uninterrupted history of something as it exists across space-time. Because once space and time are combined into a single structure, describing an object at just one instant is no longer enough. You need to describe where it is and when it is, and then how that position changes as time progresses. When you connect all of those points together, you get something more complete. That complete path is called a world line. A world line is the trajectory of an object through space-time. It includes every event associated with that object, every position it occupies at every moment along its history. Instead of imagining an object as something that exists only now, you begin to see it as something extended through time, forming a continuous line. For something that appears stationary like a chair sitting in a room, its world line is actually quite simple. It stays in the same place in space, but time continues to move forward. So its path through space-time is a straight line pointing in the time direction. It does not wander through space, but it still progresses through time. For something that moves, like a person walking across a room, the world line tilts. It changes position in space as time advances. The faster the motion through space, the more the world line leans away from the purely time-directed path. This idea might sound abstract at first, but it is actually very concrete. Think about your own life. Right now, you are at a specific location, at a specific time. A moment later, you're still somewhere, but at a slightly later time. Connect all of those points together, and you get a continuous path that represents your existence through space-time. That path is your world line. What makes world lines especially useful is that they do not depend on the idea of a universal present. They do not require a shared now to make sense. Each world line exists independently, tracing out the history of an object regardless of how different observers might slice time into moments. This becomes important when you consider how different observers describe events. In the earlier discussion about simultaneity, we saw that observers moving relative to each other disagree about which events are happening at the same time. They draw different slices through space-time, grouping events differently into what they call now. But world lines remain intact across all these perspectives. An object's world line is the same physical path, no matter how it is described. What changes is how that path is divided into moments. One observer might say that 2 points on different world lines belong to the same instant, while another observer might not. But the underlying structure, the world lines themselves, do not change. This provides a more stable way of thinking about time. Instead of trying to identify a global present, you focus on the relationships between events along world lines. Each observer experiences time along their own path, measuring intervals between events that occur on that path. This measurement is called proper time, and it is what a clock moving with the observer would record. Proper time is personal. It does not depend on distant events or how they are synchronized. It depends only on the path taken through space-time. Two observers following different world lines can measure different amounts of elapsed time between the same pair of events, especially if their paths involve different motions or gravitational effects. This is not an inconsistency. It is a direct consequence of how space-time is structured. You can imagine two travelers who start together, take different routes, and then meet again. One might have moved faster, or taken a path that involves strong gravitational fields, while the other followed a more direct route. When they compare clocks, they may find that different amounts of time have passed for each of them. Their world lines connect the same starting and ending events, but the lengths of those paths through space-time are not the same. So time, in this sense, becomes something measured along world lines, not something that flows uniformly across the universe. This perspective shifts the focus away from global synchronization and toward local experience. Each observer carries their own clock, their own sequence of events, their own sense of duration. These individual timelines do not need to align into a single universal timeline. They only need to be consistent within the framework of spacetime, and that framework provides the rules for how different observers' measurements relate to each other. One way to think about it is to imagine a map. A map can be drawn in different ways, using different projections, scales, or coordinate systems. Two maps of the same region might look different, but they still represent the same underlying geography. Similarly, different observers describe spacetime using different coordinates, different definitions of simultaneity, but they are all describing the same set of world lines. The differences lie in how those world lines are interpreted, not in the world lines themselves. This becomes especially important when considering the idea of now. If you try to define now as a set of events across different world lines, you run into the problem of simultaneity. Different observers will choose different sets. There is no unique way to select a single slice that everyone agrees on. But if you focus on a single world line, the idea of now becomes clearer. At any point along your world line, you can identify the event you are currently experiencing. That event is your now. It is local, immediate, and well-defined. It does not depend on distant events or how they are ordered by other observers. So while there is no universal present that spans the entire universe, there is a local present for each observer, tied to their position along their world line. This local perspective avoids the contradictions that arise when trying to define a global now. It also aligns with how we actually experience time. You do not directly experience distant events as part of your present. You experience what is happening at your location, at your moment along your world line. Everything else is inferred, reconstructed, or delayed by the time it takes for signals to reach you. From this point of view, the universe is not divided into a series of shared moments, but into a network of intersecting world lines, each carrying its own sequence of events. These world lines can cross, interact, and influence each other. When they do, events are connected, and causality is preserved. But between those interactions, each path evolves according to its own proper time. This makes the structure of reality less like a synchronized sequence of frames and more like a collection of trajectories woven together. And once you start thinking in terms of world lines, the earlier question about whether there is a single, shared now becomes less central, because the universe does not need one. What it needs is consistency in how events are connected, how signals travel, and how observers measure their own time along their paths. Spacetime provides that consistency, even if it does not provide a universal present. Try for a moment to imagine freezing the entire universe at once. Not just your surroundings, not just your city or your planet, but everything. Every galaxy, every star, every particle, all held in a single, perfectly defined instant. It feels like a reasonable idea. After all, that is exactly how we tend to picture time, as if reality could be paused like a video, revealing a single frame that represents what exists right now. But once spacetime enters the picture, that idea becomes much harder to justify. Because to freeze the universe, you first need to define what counts as a single moment across all of space. You need a rule that says these events belong to the same instant, even if they are separated by vast distances. In classical physics, that rule was straightforward. Time was universal, so any event with the same time coordinate belonged to the same moment. You could, at least in principle, construct a global slice of the universe. Relativity removes that possibility. What replaces it is not confusion, but a kind of flexibility that makes a single universal slice impossible to define without choosing a specific point of view. Every observer can still describe the universe, but each one does so by selecting their own way of grouping events into moments. Those groupings are consistent within their frame of reference, but they do not match those of other observers moving differently. This is what it means to say there is no universal slice of the universe. To understand it more clearly, consider again how observers define simultaneity. Each observer constructs a set of events they consider to be happening at the same time. That set forms a slice through spacetime, but because simultaneity depends on motion, different observers construct different slices. These slices are not minor variations of one another. They can differ in a way that shifts events between what one observer calls the past and what another calls the future. Imagine two distant events, A and B. For one observer, A and B might lie on the same slice, meaning they are simultaneous. For another observer moving relative to the first, event A might occur before B. For yet another observer, B might occur before A. There is no contradiction here, because none of these observers is making a mistake. They are simply using different definitions of simultaneity, all of which are valid within the framework of relativity. But this leads to an important consequence. If there is no single, observer-independent way to define simultaneity, then there is no single, observer-independent way to define a global now. The universe does not come equipped with a preferred slicing into moments. Any such slicing must be chosen relative to an observer's motion. You can think of it like trying to cut a loaf of bread. In classical physics, there is one natural way to slice it, straight across, producing even pieces that represent successive moments in time. In relativity, there are infinitely many ways to slice it, each corresponding to a different observer. Some slices might be straight, others tilted, but none is singled out as the correct one by the laws of physics. Each slice intersects the same underlying structure, but it groups events differently. This becomes especially significant when considering very distant regions of the universe. Events that are far apart in space cannot influence each other immediately, because signals cannot travel faster than light. That means their temporal ordering is not fixed in an absolute sense. Different observers can legitimately disagree about whether one event occurs before another, as long as those events are outside each other's light cones. So for widely separated events, the question, which one is happening now, does not have a unique answer. Instead, it depends entirely on how you choose to define your slice through spacetime. This is not just a limitation of measurement, it is built into the structure of the universe. There is no hidden, deeper layer where all events line up into a single universal present. The lack of a preferred slice is a fundamental feature of spacetime. It also means that the idea of the universe evolving through a sequence of global moments becomes difficult to maintain. In classical thinking, you could imagine the universe as a series of snapshots, each representing a complete state at a given time. One snapshot follows another, creating a timeline that moves forward. But in relativity, there is no unique way to define those snapshots. Different observers would construct different sequences. So instead of a single sequence of moments, you have a structure that contains all events, with different observers tracing different paths and defining different slices. This shift can feel subtle at first, but it has deep implications. It means that the present moment, as a global feature, is not something the universe provides. It is something observers define locally, based on their motion and their method of synchronization. Each observer can still talk about their own now, the set of events they consider simultaneous. But that now is not shared universally. It does not extend across the entire universe in a way that everyone agrees on. And importantly, this does not lead to chaos or inconsistency. The laws of physics ensure that all observers can translate their descriptions into one another's frames of reference. Even though they disagree about simultaneity, they agree on the relationships between events, on causality, and on measurable quantities like proper time along world lines. So the structure remains coherent even without a universal slice. What disappears is the idea that there is a single, objective present that applies everywhere at once. In its place, we are left with a more nuanced picture, The universe is not divided into a sequence of global moments, but into a network of events connected by space-time relationships. Observers move through this network, constructing their own versions of time as they go. If you follow the logic of space-time just a little further, something unusual begins to take shape, not in a dramatic or sudden way, but gradually, almost reluctantly, as if the picture is assembling itself whether you're comfortable with it or not. Up to this point, we have moved away from the idea of a shared now, and we have seen that different observers slice space-time differently. We have also seen that events are best described as points in a four-dimensional structure, rather than as parts of a sequence unfolding moment by moment. The next step is to ask a simple question. If all events can be located within space-time, and if there is no preferred present moment, then what exactly is the status of the past and the future? In everyday thinking, the answer feels obvious. The past has already happened. It is fixed, recorded in memory and history. The future has not happened yet. It is open, uncertain, waiting to unfold. And the present is the boundary between the two, the moving edge where reality is being created. But this picture depends entirely on the idea of a universal now. Once that idea is removed, the distinction between past, present, and future becomes less clear. Because without a shared present, there is no single boundary that separates what exists from what does not. This is where the block universe model enters. The block universe is not a separate theory added on top of relativity. It is a way of interpreting what relativity already implies. If space-time is a four-dimensional structure containing all events, and if no particular slice of that structure is privileged, then one natural conclusion is that all events exist equally within that structure. In this view, the universe is like a complete geometric object. It does not grow, it does not update, and it does not unfold in the way we usually imagine. Instead, it simply is. Every event, whether we would call it past, present, or future, is located somewhere within this structure, defined by its spacetime coordinates. You can think of it as a kind of four-dimensional map. If you look at a map of a city, all locations exist on that map at once. The streets, the buildings, the intersections, they are all there, regardless of whether you're currently standing on them. Your experience of moving through the city does not change the map itself. It only changes your position within it. The block universe applies a similar idea to time. Your life from beginning to end can be represented as a path through space-time. Every moment of that life corresponds to a point along your world line. From your perspective, you experience those moments one after another. But from the perspective of the block universe, all of those moments exist together as part of the same structure. Nothing is being added to the universe as time passes. Instead, your experience of time is the process of moving along your world line, encountering events in a particular order. This leads to a shift in how we think about change. In the usual picture, change is something that happens as time moves forward. The universe evolves from one state to another. In the block universe, change is represented by differences between different regions of space-time. One part of the structure contains one configuration, another part contains a different configuration, and the relationship between them encodes what we perceive as change. The passage of time in this view is not something that happens to the universe as a whole. It is something that happens within the experience of observers moving through it. This can feel counterintuitive, because it suggests that the future is not something that comes into existence later, but something that already exists in the structure of space-time. At first, that might sound like it removes the sense of openness or uncertainty we associate with the future. But the model itself does not necessarily dictate how we experience or predict events. It simply describes how events are arranged within space-time. From within the block, observers still have limited information. They do not know what lies ahead along their world line. They make decisions, form expectations, and experience outcomes as they occur. The structure contains all events, but the experience of those events remains sequential and local. One way to make this clearer is to think about a film reel. A film consists of many frames, each one capturing a moment in the story. All of those frames exist at once on the reel. The entire story is already there. But when the film is projected, the frames are shown one after another, creating the experience of motion and progression. In the block universe, spacetime is like the full reel. Your consciousness is like the projector, moving along the sequence of events and experiencing them in order. This analogy is not perfect, but it captures the key idea. The structure itself does not change. What changes is your position within it. Now bring this back to the question of now. In the block universe, there is no single, global, present moment that divides the universe into what exists and what does not. All events exist within the block. The present is not a special slice of reality. It is a feature of how observers experience their position along their world line. Each observer has their own now, corresponding to the event they are currently experiencing. But that now is not a universal property. It does not extend across the entire structure in a way that everyone agrees on. Different observers, moving differently, will associate different sets of events with their present moment, just as we saw with the relativity of simultaneity. So the block universe does not restore the idea of a shared present. It removes the need for one entirely. Instead of asking what is happening now across the universe, the model encourages a different question. How are events arranged within space-time, and how do observers move through them? This shift can feel subtle, but it changes the role of time. Time is no longer a flowing entity that carries the universe forward. It becomes part of the structure, a dimension that allows events to be ordered and related, but not something that evolves independently. And yet, even within this model, the feeling of a present moment does not disappear. You still experience a now. You still distinguish between past and future. You still feel as though time is moving forward. The block universe does not deny that experience. It simply places it within a broader framework where that experience arises from your path through space-time rather than from a universal process. This raises an important question. If the block universe suggests that all events exist within a single structure, why does it feel as though time flows? Why does the present seem to move, even if the underlying structure does not? By this stage, the question has shifted from intuition to something more precise. Instead of asking what now feels like, it becomes more useful to ask what the equations of physics actually require, and just as importantly, what they do not mention at all. Because if now were a fundamental part of the universe, you would expect it to appear clearly in the laws that describe how the universe works. But when you look at those laws, something curious happens. The word now never shows up, not in classical mechanics, not in relativity, not in quantum field equations. Physics does not include a variable labelled present moment, and it does not assign any special status to a particular slice of time. Instead, it works with relationships between events, coordinates in space-time, and quantities that remain consistent across different observers. This absence is not an oversight. It reflects something deeper about how physical theories are constructed. The goal of physics is to describe how systems behave, how quantities change, and how events are related. It does this using mathematical structures that remain valid regardless of who is observing or where they are. A universal now would introduce a preferred frame, a special perspective that all observers must agree on. But one of the central lessons from relativity, developed by Albert Einstein, is that no such preferred frame exists. All inertial observers are equally valid. That means the laws of physics must look the same to each of them, even if they are moving relative to one another. If the equations were to include a special observer-independent present moment, they would violate this principle. They would single out one way of slicing space-time as the correct one, which relativity does not allow. So instead, physics avoids defining now altogether. It works with events. An event is a point in space-time defined by its coordinates. You can label it, measure it, and relate it to other events, but you do not need to say whether it is part of a universal present. You only need to know where and when it occurs relative to other events. From this perspective, the universe is not evolving through a sequence of nows. It is described as a collection of events connected by physical laws. Those laws tell you how one event can influence another, how signals propagate, how fields change, and how particles move. They provide a structure that links events together, but they do not require a moving present moment to do so. This becomes clearer when you look at how time appears in equations. In classical mechanics, time is often treated as a parameter that tracks change. It allows you to describe how position, velocity, and other quantities vary. But even there, time does not come with a built-in now. It is simply a coordinate that can be measured and compared. In relativity, time becomes even more flexible. Different observers assign different time coordinates to the same event depending on their motion. The equations are constructed so that these differences are consistent and predictable. They transform smoothly from one frame to another, ensuring that physical laws remain the same. But again, there is no preferred time coordinate that represents the true present. Each observer defines their own, so instead of a single timeline, physics provides a framework for translating between many timelines. This leads to an important distinction. Physics describes how events are ordered when they are causally connected. If one event can influence another, then all observers will agree on their order, because always precedes effect. This ordering is preserved across all frames of reference, but for events that are not causally connected, events that lie outside each other's light cones, there is no absolute order. Different observers can disagree about which event happened first, and the laws of physics allow for that. This is not a gap in the theory, it is a feature. It means that the universe does not impose a global sequence on all events. It only enforces consistency where it matters, where interactions occur. From this point of view, now becomes something that is not required for the universe to function. You do not need a universal present to describe motion, forces, or interactions. You only need the relationships between events and the rules that govern those relationships. This is why physics can operate perfectly well without ever defining now. It can predict outcomes, describe systems, and explain observations without invoking a shared present moment. Everything that needs to be calculated can be expressed in terms of coordinates, intervals, and transformations. The idea of now simply does not enter into those calculations, and yet, despite its absence from the equations, the experience of now remains very real. You feel it, you identify with it. It seems to be the point where everything happens, so there is a gap between what physics describes and what you experience. Physics gives you a structure of space-time, a network of events connected by laws, with no preferred present. Experience gives you a moving sense of now, a moment that feels special and immediate. Bridging that gap requires a shift in perspective. Instead of asking where now exists in the universe, it becomes more useful to ask where now exists in the relationship between an observer and the events they encounter. Because while physics does not define a universal present, it does define something else. It defines how observers move through space-time, how they measure time along their own paths, and how they experience sequences of events locally. That local experience may not correspond to a global feature of the universe, but it is still grounded in physical processes. So the question is no longer whether now exists in the equations. The question becomes how the feeling of now arises from a universe that does not include it as a fundamental ingredient, and how that local sense of the present fits into the broader structure defined by space-time. Start from something very close to you, something you don't need to imagine or reconstruct. Not distant stars, not observers moving at extreme speeds, just the quiet, steady passage of time that you personally experience. The seconds that pass for you right now feel consistent. Your thoughts move forward, your breathing continues, your awareness progresses in a smooth and uninterrupted way. Nothing about it suggests flexibility or disagreement. It feels like time is doing exactly one thing, moving forward at a fixed pace. That experience is not an illusion in the sense of being false. It is real, but it is also local. It belongs to you, specifically to the path you're taking through space-time. And in physics, that personal measure of time has a name. It is called proper time. Proper time is the time measured along a world line. It is what a clock would record if it were moving together with you, sharing your exact motion through space-time. It does not depend on distant events, on synchronization with other clocks, or on how other observers describe the situation. It is the most direct, most personal measure of time available in relativity. You can think of it as your own timeline, the sequence of moments that you personally experience as you move through the universe. This idea becomes especially important once the notion of a universal clock has been removed. In classical physics, time was the same for everyone, or you could compare clocks anywhere in the universe, and in principle they would all agree. Proper time was not a necessary concept because there was only one time to measure. Relativity changes that completely. Once time becomes dependent on motion and gravity, there is no longer a single timeline shared by all observers. Instead, each observer carries their own clock, their own measure of time, tied to their specific path through space-time, and that path, your world line, determines how much time passes for you. To understand how this works, imagine two observers who start together at the same event. They synchronize their clocks, confirm that they agree, and then move apart following different paths through space-time. One might remain relatively stationary, while the other travels at high speed or moves through regions of strong gravity. Eventually they meet again and compare their clocks. According to classical intuition, both clocks should show the same amount of elapsed time. After all, they started together and ended together, but relativity predicts something different. The amount of proper time experienced by each observer depends on the path they took. One observer may have experienced less time than the other. Their clock will show a smaller reading. This is not a malfunction or an error. It is a real physical effect, confirmed by experiments involving high-speed particles and precise atomic clocks. The difference arises because the geometry of spacetime assigns different lengths to different paths between the same events. That idea might sound unusual at first, but it becomes clearer with a comparison. In ordinary space, the distance between 2 points depends on the path you take. The shortest distance is a straight line, but if you take a curved path, the distance increases. In space-time, something similar happens, but with time instead of distance. Different paths between the same two events can result in different amounts of proper time. This leads to a subtle but important shift. Time is no longer something that flows uniformly in the background. It becomes something measured along paths. The passage of time depends on how you move, not just where you are. So when you ask, how much time has passed? The answer is incomplete unless you specify whose time you are measuring. Proper time provides that specification. It anchors time to the observer, making it a local quantity rather than a global one. Each observer's experience of time is tied to their world line, and different world lines can yield different amounts of elapsed time between the same pair of events. This has direct impact on how we think about now. In the absence of a universal present, proper time gives each observer a well-defined sequence of moments. At any point along your world line, there is a specific event that represents your current state. That event is your now. But this now does not extend across the universe. It is not a slice that includes distant events in a way that everyone agrees on. It is a point, local and specific, defined by your position in space-time. Everything else, all other events, are related to that point through the structure of space-time, but they are not part of a shared present. This means that while the idea of a global now disappears, the idea of a personal now remains intact. You always have a present moment, but it is yours alone, tied to your path through space-time. This distinction helps resolve the tension between physics and experience. Physics tells us that there is no universal present. Experience tells us that there is always a present moment. Proper time bridges that gap by showing that the present is not a global feature of the universe, but a local feature of an observer's trajectory. It also clarifies how time can behave differently for different observers without leading to contradictions. Each observer measures time along their own world line, and those measurements are consistent within their frame of reference. When observers compare their results, the differences can be explained by the geometry of space-time, without requiring a single, shared timeline. This is why time dilation does not feel strange to the observers experiencing it. If you were travelling at high speed, your own clock would tick normally. You would not notice anything unusual about your passage of time. The difference only appears when your clock is compared to another observer's clock, one that followed a different path. So proper time is both simple and profound. It is simple because it corresponds directly to what you experience. It is the time measured by your own clock, the sequence of moments you live through. It is not abstract or indirect. But it is also profound because it replaces the idea of a universal timeline with a collection of personal timelines, each tied to a specific path through space-time. And once you accept that, the structure of time begins to look less like a single flowing river and more like a network of paths, each carrying its own measure of duration. Some paths may involve rapid motion, others strong gravitational fields, and these differences affect how much time passes along them. The universe does not enforce a single rate of time. It allows for variation, as long as the relationships between events remain consistent. A quiet shift happens when you stop asking whether time is shared, and begin asking how fast it passes for different observers. Not in a metaphorical sense, not in the way time feels fast or slow depending on your mood, but in a strictly physical sense, how much time actually passes between two events when measured by different clocks. Because once proper time is introduced, the next natural question is unavoidable. If each observer carries their own clock along their world line, do all those clocks always agree? The answer, as it turns out, is no. And this is where time dilation enters, not as a strange exception, but as a direct consequence of how space-time is structured. Time dilation describes the way time passes at different rates for observers in relative motion. It is not a trick of perception, not a limitation of measurement, but a measurable, repeatable effect that has been confirmed in experiments many times over. To approach it gently, imagine two identical clocks. They start together, side by side, perfectly synchronized. At that moment, there is no difference between them. They tick at the same rate, marking time in the same way. Now suppose one of those clocks begins to move at a high speed, while the other remains at rest. From the perspective of the stationary observer, something subtle begins to happen. The moving clock appears to tick more slowly. Each second on that clock takes slightly longer compared to the stationary one. The faster the motion, the more pronounced the effect becomes. This is not because the clock is damaged or malfunctioning. If you were travelling along with that moving clock, it would seem perfectly normal. It would tick steadily, just as it always does. You would not feel anything unusual about your own passage of time. The difference only appears when the two clocks are compared from a common reference. That comparison reveals that less time has passed along the path of the moving clock. This effect follows directly from the requirement that the speed of light must remain constant for all observers. To see why, consider a simple kind of clock, one that measures time using light itself. Imagine a device where a beam of light bounces between two mirrors. Each round trip of the light counts as one tick of the clock. If the clock is at rest, the light travels straight up and down between the mirrors. The distance is fixed, and the time for each tick is determined by the speed of light. Now imagine that the clock is moving sideways relative to an outside observer. From the perspective of that observer, the light no longer travels straight up and down, it follows a diagonal path, because while it moves between the mirrors, the entire clock is also moving sideways. The light has to cover more distance in order to complete each tick, but the speed of light remains the same, so if the distance increases and the speed stays constant, the time for each tick must increase as well. The clock ticks more slowly. This is not a special property of that particular clock. It applies to any process that measures time, because all physical processes are governed by the same underlying laws. Chemical reactions, biological processes, atomic vibrations, everything slows down in exactly the same way when observed from a different frame of reference. Time itself is what is being affected. This leads to a situation where two observers, moving relative to each other, each see the other's clock running slow. At first, this might seem contradictory. How can both observers see the other's time as slower? The resolution lies in the relativity of simultaneity. Each observer is using their own definition of now to compare clocks. Because those definitions differ, the comparisons are not symmetric in the way classical intuition expects. The differences in simultaneity ensure that there is no contradiction, even though the situation appears symmetrical. The important point is that time dilation is not about one observer being right and the other being wrong. It is about the fact that each observer's measurement of time is tied to their own world line. Proper time, the time measured along a path, depends on the path itself. So when two observers follow different paths through space-time, they accumulate different amounts of proper time, even if they start and end at the same events. This becomes especially clear in a scenario often referred to as the twin paradox. Imagine two twins. One remains on Earth, while the other travels in a spacecraft at a very high speed, eventually turning around and returning home. When they reunite, the travelling twin has aged less than the one who stayed behind. From the perspective of the twin on Earth, the explanation is straightforward. The travelling twin was moving at high speed, so their time was dilated. Their clock ran slower, and less time passed for them. From the perspective of the travelling twin, the situation is more complex because their motion involves acceleration when turning around. This breaks the symmetry between the two observers and leads to a consistent explanation in which the travelling twin experiences less proper time overall. The key idea is that the amount of time experienced depends on the path through space-time. Different paths yield different durations, so time dilation is not just a theoretical concept. It has real, measurable consequences. Clocks on fast-moving airplanes tick slightly slower than those on the ground. Particles moving at high speeds in accelerators live longer than they would at rest, because their internal processes are slowed by time dilation. Even the systems that allow your phone to determine its position using satellites must account for these effects to remain accurate. Without those corrections, the errors would accumulate quickly. So when we say that time can slow down, we're not speaking metaphorically. We are describing a precise physical effect, one that depends on motion and is built into the structure of space-time. Now bring this back to the idea of now. If time passes at different rates for different observers, then their sequences of moments do not align in a simple way. One observer's now does not correspond neatly to another's, not just because of simultaneity, but because their clocks are progressing at different rates. This deepens the breakdown of a universal present. Not only do observers disagree about which events are simultaneous, they also accumulate time differently as they move through space-time. Their personal timelines stretch and compress relative to one another. And yet, from within each timeline, everything feels normal. Your own proper time is always consistent. Your thoughts, your experiences, your sense of duration all proceed smoothly along your world line. There is no internal sign that your time is being dilated relative to someone else's. This creates an interesting contrast. From the outside, time can appear flexible, stretching and compressing depending on motion. From the inside, it always feels steady. So the slowing of now is not something you directly feel. It is something that emerges when comparing different observers. Each observer carries their own now forward along their world line, experiencing time at a consistent rate locally, even if that rate differs from others when viewed from a different frame. This reinforces the idea that now is not a universal feature of the universe. It is a local feature of an observer's experience tied to their motion and their path through space-time. And once motion alone is enough to alter the rate at which time passes, it becomes natural to ask what happens when gravity enters the picture. Begin with a simple comparison that does not require high speeds or distant galaxies. Imagine two identical clocks again, synchronized carefully, placed at different heights. One sits on the floor, the other is placed on a shelf slightly above it. Nothing else changes. They are not moving relative to each other in any noticeable way. They are simply at different positions within a gravitational field. If classical physics were the full story, those clocks would remain in perfect agreement forever. Height would not matter. Gravity would pull on objects, influence motion, but it would not reach into time itself and alter how quickly moments pass. But once Albert Einstein extended his earlier work into what became general relativity, that expectation had to be revised. Because in this deeper description of the universe, gravity is no longer treated as a force acting across space. Instead, it is understood as a curvature of space-time itself. Massive objects like planets, stars and galaxies change the geometry of space-time around them. They do not simply pull on things, they reshape the paths that objects follow. And those paths include the paths of clocks. So when you place one clock closer to a massive object and another slightly farther away, they are no longer following identical paths through space-time. Even if they appear stationary relative to each other, their positions within the curved geometry are different, and that difference affects how time passes. The clock closer to the massive object, deeper in the gravitational field, ticks more slowly than the one farther away. This effect is called gravitational time dilation. Just like the time dilation caused by motion, it is not a matter of perception. Each clock measures its own proper time normally. There is no internal signal that anything unusual is happening. The difference only appears when the clocks are compared. But when they are compared, the result is clear. Less time has passed for the clock deeper in the gravitational field. At first, this might seem like a small correction, something that only matters in extreme environments, but the effect is always present. Even on Earth, time passes slightly more slowly at sea level than it does on a mountaintop. The difference is tiny, far too small to notice in daily life, but it has been measured with extremely precise instruments. Atomic clocks placed at different altitudes tick at slightly different rates, exactly as predicted by general relativity. So gravity, like motion, alters the rate at which time passes. And this adds another layer to the question of now. Because if time flows differently depending on gravitational conditions, then observers located in different gravitational environments do not just disagree about simultaneity. They also accumulate time at different rates, even if they remain at rest relative to one another. Consider a more dramatic example. Imagine one observer far from any massive object, in deep space, and another observer near the surface of a very dense star. The observer near the star experiences a stronger gravitational field. Their clock ticks more slowly compared to the one far away. If they were to compare their clocks after some time, they would find that the observer near the star has experienced less time. From the perspective of the distant observer, everything near the star appears to be running slow. Processes take longer. Clocks tick more slowly. Even light emitted from near the star is shifted in frequency due to the gravitational field. But from the perspective of the observer near the star, everything feels normal. Their own clock ticks steadily. Their surroundings behave as expected. It's only when they compare their measurements with those from a different gravitational environment that the difference becomes apparent. So once again, time proves to be local. It depends not only on motion, but also on position within a gravitational field. Each observer carries their own proper time, shaped by the path they follow through curved spacetime. This reinforces the idea that there is no universal timeline. If both motion and gravity affect the rate at which time passes, then there is no single clock that can represent the entire universe. Any attempt to define a global now would have to account for these differences, but there is no natural way to do so that all observers would agree on. Instead, the structure of space-time allows for many different rates of time, all consistent within the same framework. This can be visualized by thinking about space-time as a landscape rather than a flat surface. In flat space-time, the geometry is simple, and the differences in time arise mainly from motion. In curved space-time, the geometry itself varies from place to place. The presence of mass and energy bends space-time, creating regions where time flows at different rates. Objects and observers move through this landscape along paths determined by the curvature. Those paths are still world lines, but now they are influenced by gravity as well as motion. The proper time along each path depends on both factors. This means that two observers who start together and end together can experience different amounts of time, not only because of how they move, but also because of where they travel. And importantly, there is no way to define a single universal now that accounts for all of these variations. If you tried to construct such a now, you would have to decide how to compare clocks at different positions in a gravitational field, how to synchronize them, and how to account for the curvature of space-time. Any method you choose would depend on a particular frame of reference, and other observers would not necessarily agree with it. So the idea of a shared present becomes even more difficult to maintain. Instead of a single moment that spans the universe, you have a patchwork of local times, each tied to an observer's position and motion. And yet, as before, each observer experiences a perfectly consistent flow of time along their own world line. From the inside, nothing feels distorted. This creates a layered picture. On one level, time is deeply flexible, affected by motion and gravity, varying across different regions of space-time. On another level, time is steady and continuous for each observer, providing a consistent framework for experience. The tension between these two perspectives is not a contradiction. It is a reflection of how space-time works. General relativity does not remove time. It embeds time within a dynamic structure that responds to mass and energy. It allows different observers to experience different rates of time while preserving the consistency of physical laws. Take the earlier idea of clocks ticking at different rates and extend it just a little further, not by adding new principles, but simply by allowing gravity to become stronger and more uneven. What begins as a subtle difference between clocks at slightly different heights gradually turns into something much harder to ignore. Because once gravitational time dilation becomes significant, the idea that different observers can share a meaningful now begins to fail in a very direct and unavoidable way. Start with a situation that still feels somewhat familiar. Imagine two observers again, but this time one remains far from any massive object, while the other moves closer to something much denser, perhaps a neutron star. The gravitational field near that object is far stronger than anything experienced on Earth. Space-time is curved more sharply, and the rate at which time passes is affected more noticeably. From the perspective of the distant observer, the clock near the neutron star ticks slowly. Not metaphorically, not in appearance, but in a measurable sense. If they could watch that clock from afar, they would see each second take longer compared to their own. Signals sent from near the neutron star arrive stretched out in time. Processes appear to unfold more slowly. The deeper the observer is in the gravitational field, the more pronounced the effect becomes. But from the perspective of the observer near the neutron star, nothing unusual is happening. Their own clock ticks steadily. Their thoughts proceed at a normal pace. Their surroundings behave as expected. If they drop an object, it falls. If they measure time locally, everything appears consistent. So once again, time is behaving differently depending on where you are. Now consider what happens when these two observers try to compare their sense of now. The distant observer might attempt to define a present moment that includes both their own current event and some event occurring near the neutron star. But which event near the star corresponds to that moment? Because the clock near the star is running slower, its sequence of events is stretched relative to the distant observer's timeline. The distant observer might say that a particular event near the star is happening now, but the observer near the star would not agree that this event is part of their present in the same way. If the observer near the star tried to define their own now, it would correspond to a different set of distant events. The disagreement is not just about simultaneity in the sense of relative motion. It is now influenced by gravity, by the curvature of space-time itself. And as the gravitational field becomes stronger, the disagreement becomes more extreme. To see how far this can go, imagine moving even closer to an object where gravity is intense enough to significantly distort space-time, something like the region near a black hole. Near such an object, gravitational time dilation becomes dramatic. From the perspective of a distant observer, a clock approaching the black hole appears to slow down more and more. As it gets closer to the event horizon, the boundary beyond which nothing can escape, the clock seems to tick increasingly slowly, approaching a standstill. Light signals from that clock take longer and longer to arrive. Each successive signal is delayed more than the last. To the distant observer, it appears as though time near the event horizon is almost frozen. But again, from the perspective of the observer falling toward the black hole, nothing special happens at that boundary. Their own proper time continues normally. They cross the event horizon without noticing anything unusual locally. Their clock ticks at a steady rate. Their experience flows continuously. This creates a striking situation. Two observers, both following the laws of physics correctly, describe time in radically different ways. For the distant observer, events near the event horizon slow down and almost stop. For the infalling observer, those same events proceed without interruption. Now consider the idea of a shared now between these two observers. From the distant observer's perspective, the infalling observer never quite reaches the event horizon. They appear to approach it more and more slowly, taking an infinite amount of time to cross it. From the infalling observer's perspective, they cross the event horizon in a finite amount of time and continue inward. So which event corresponds to the present moment shared by both observers? There is no consistent answer. Any attempt to define a single now that includes both observers leads to contradictions. The structure of space-time simply does not allow for a global present that both observers can agree on. This is what it means for gravitational time dilation to contribute to the breakdown of now. It is not just that clocks tick at different rates. It is that the differences become so large and so dependent on position that the idea of synchronizing time across space becomes meaningless. In regions of strong gravitational curvature, space-time itself is arranged in such a way that different observers cannot construct a common present moment. Each observer's proper time defines their own sequence of events, their own progression through space-time. Those sequences do not align into a single shared timeline. Instead, they form a network of paths, each with its own rate of time, each influenced by the curvature of space-time. This reinforces a pattern that has been building from the beginning. First, motion disrupted the idea of a universal now through the relativity of simultaneity. Then, proper time showed that each observer carries their own timeline. Now, gravity adds another layer, making those timelines diverge even more depending on where observers are located. At no point does the universe provide a mechanism to restore a shared present. Instead, every step moves further away from that idea. And yet, from within each observer's experience, time remains smooth and continuous. The observer near the neutron star does not feel their time slowing down. The observer falling toward a black hole does not experience time freezing. Each one experiences a consistent flow of proper time along their world line. So the breakdown of now is not something you feel internally. It is something that emerges when comparing different observers, especially when they occupy very different regions of space-time. This distinction is important. It means that the absence of a universal present does not disrupt the consistency of experience. It only challenges the idea that there is a single moment that everyone shares. Instead, the universe allows for many local nows, each tied to an observer's position and motion, each valid within its own context. And when gravity becomes strong enough, those local nows can diverge so significantly that trying to connect them into a single global moment becomes not just difficult, but impossible. Consider a region of the universe where the effects we've been discussing are no longer subtle corrections, but dominant features that shape everything about how time behaves. Not just slightly slower clocks or minor disagreements between observers, but situations where the very structure of space-time becomes so distorted that familiar ideas about before, after, and now begin to lose their usual meaning. This is where black holes enter the picture. A black hole is not simply an object with strong gravity. It is a region of space-time where curvature becomes extreme, where the geometry itself is altered so significantly that paths through space-time behave in ways that have no everyday counterpart. To approach this carefully, it helps to avoid dramatic imagery at first, and instead focus on what happens to time. Far from a black hole, space-time is only gently curved. Clocks tick at rates that are nearly identical, and the differences we discussed earlier remain small, but as you move closer to a black hole, the curvature increases, and with it the effect on time becomes stronger. From the perspective of an observer far away, something remarkable happens. A clock that moves toward a black hole appears to slow down more and more as it approaches the event horizon. Each tick takes longer to complete when viewed from a distance. Light signals emitted from the clock arrive increasingly stretched out in time, with larger and larger gaps between them. If you were watching such a clock from far away, you would see it approach the event horizon, but never quite reach it. Its motion appears to slow, its signals become more delayed, and eventually it seems to freeze in place, fading gradually as the light it emits becomes weaker and more red-shifted. From that distant perspective, time near the event horizon appears to almost stop, but now shift your attention to the observer falling toward the black hole. For that observer, nothing like this freezing occurs. Their clock ticks normally, their experience of time remains steady. They cross the event horizon in a finite amount of proper time, without encountering any sudden barrier or abrupt change at that boundary. So we now have two very different descriptions of the same situation. From far away, the infalling observer never seems to cross the event horizon. From their own perspective, they cross it without difficulty. This is not a contradiction. It is a reflection of how space-time is structured around a black hole. The key point is that different observers are using different coordinate systems, different ways of slicing space-time into moments. Near a black hole, these differences become extreme. The distant observer's notion of now stretches out near the event horizon. Events that occur closer and closer to that boundary are assigned times that grow larger and larger, making it seem as though those events are delayed indefinitely. The infalling observer's notion of now remains local and continuous, following their world lines smoothly across the horizon. Because these two perspectives are so different, the idea of a shared now between them becomes impossible to maintain. There is no single moment that both observers can agree corresponds to what is happening right now at the event horizon. This is the breakdown of now in one of its most extreme forms. It is not just that observers disagree slightly. It is that their definitions of time diverge so strongly that attempting to align them into a single present moment no longer makes sense. To see this more clearly, consider what it would mean to define a global now that includes both the distant observer and the infalling one. You would need to choose a slice of space-time that passes through both observers at once. But any such slice depends on a choice of coordinates, a choice of how to define simultaneity. One choice might align with the distant observer's perspective, assigning the infalling observer a time that never quite reaches the event horizon. Another choice might align more closely with the infalling observer's perspective, allowing them to cross the horizon in finite time. Neither choice is more correct than the other. They are simply different ways of describing the same spacetime. And because there is no preferred choice, there is no preferred now. This situation becomes even more striking when you consider what happens inside the event horizon. Once an observer crosses that boundary, all possible future paths lead further inward, toward the central region of the black hole. The structure of space-time is such that moving forward in time inevitably means moving toward the center. In a sense, the roles of space and time begin to shift. The direction that once represented time continues to point inward, while directions that once represented space take on different roles. This does not mean that time disappears, but it does mean that the familiar distinction between space and time becomes less intuitive. From the perspective of an outside observer, the interior of the black hole is effectively disconnected from the rest of the universe. No signal can escape from within the event horizon to reach them. So even the concept of comparing now across that boundary becomes meaningless. There is no way to exchange information that would allow observers on opposite sides to agree on a shared present. The causal structure of spacetime prevents it. This highlights a deeper point. The idea of now relies on the ability to compare events, to say that they are happening at the same time. But such comparisons require the exchange of signals, or at least the possibility of such an exchange. In regions where spacetime is strongly curved, and especially across boundaries like event horizons, that possibility can disappear. Without the ability to relate events through signals, the notion of a shared present loses its operational meaning. So black holes do not just distort time, they reveal the limits of how time can be defined across space. They show that now is not something that can be extended arbitrarily far. It is constrained by the structure of space-time, by the paths that signals can take, and by the geometry created by mass and energy. What remains consistent is local experience. The infalling observer still experiences a continuous flow of time along their world line. The distant observer still experiences their own proper time. Each has a well-defined sequence of events, but there is no way to merge those sequences into a single, shared timeline that both would recognize as the present. This is the most extreme version of a pattern we have been building step by step. First, simultaneity became relative. Then proper time made time personal. Gravity introduced variation in the rate of time. Now, in the presence of black holes, the structure of space-time itself prevents the construction of a global now. And yet, even in these extreme conditions, the laws of physics remain consistent. They provide precise relationships between events, even if those events cannot be placed into a single universal present. So instead of a universe that unfolds moment by moment in a synchronized way, what we see is a structure where different regions, different observers, and different paths through space-time all carry their own versions of time. And in the most extreme environments, those versions can diverge so completely that the question, what is happening right now, no longer has a single, meaningful answer at all. Step back from black holes for a moment and return to something that feels much larger and at first glance more orderly. Instead of focusing on extreme regions where space-time is heavily distorted, consider the universe as a whole, spread out across vast distances, filled with galaxies, clusters, and the faint glow of ancient radiation. Because while relativity has steadily dismantled the idea of a universal now, cosmology seems, at least on the surface, to offer a way to bring something like it back. The question becomes straightforward again, but in a different context. If the entire universe is expanding in a uniform way, could there be a kind of global clock that applies everywhere? Not a clock in the Newtonian sense, but a natural time coordinate that all observers can agree on, at least in principle. This idea is often referred to as cosmic time. To understand where it comes from, begin with one of the most important observations in modern cosmology. when we look out into space, we see that distant galaxies are moving away from us. The farther they are, the faster they appear to recede. This is not because we are at a special location, but because space itself is expanding. Every region of the universe on large enough scales behaves similarly. Galaxies are not flying outward from a central point. Instead, the distances between them are increasing everywhere at once. If you were located in a different galaxy, you would see the same pattern, with other galaxies moving away from you. This uniform expansion suggests that the universe has a kind of large-scale symmetry. On average, it looks the same in all directions and from all locations. This property allows physicists to construct models of the universe that treat it as homogeneous and isotropic on large scales. Within these models, it becomes possible to define a preferred set of observers. These are observers who are at rest with respect to the overall expansion. They are not moving relative to the average motion of galaxies. They simply drift along with the expansion of space itself. For these observers, something interesting happens. They can define a time coordinate that is shared across the entire universe, based on the age of the universe since its earliest moments. This time coordinate is what we call cosmic time. It is measured by clocks carried by observers who move with the expansion, following what are called co-moving world lines. If you imagine a grid that expands along with the universe, these observers remain fixed on that grid. Their positions in space do not change relative to the large-scale structure. Only the distances between points on the grid increase. For such observers, it makes sense to talk about the universe having a common age. They can all agree on how much time has passed since the beginning of the expansion. Their clocks, if placed far from strong gravitational fields and moving only with the expansion, tick at the same rate. This seems to bring back something like a universal clock. At first glance, it looks as though cosmic time might restore the idea of a shared now, at least for these special observers. But the situation is more subtle than it appears. Cosmic time is not imposed by the fundamental laws of physics in the same way that Newton's absolute time was. It emerges from the particular structure of our universe, specifically its large-scale symmetry. If the universe were not homogeneous and isotropic, if it had a more irregular structure on large scales, then defining such a global time coordinate would be much more difficult, or perhaps impossible. Even in our universe, cosmic time applies only under certain conditions. It works well when considering the average behavior of matter and energy across vast distances. But locally, where gravitational fields vary and objects move relative to one another, proper time still differs between observers. So cosmic time does not replace proper time. It provides a convenient reference frame for describing the universe as a whole, but individual observers can still experience time differently depending on their motion and position. This means that while cosmic time offers a kind of shared timeline, it does not fully restore the idea of a universal now in the sense we started with. To see why, consider observers who are not co-moving with the expansion. If an observer is moving relative to the cosmic rest frame, their measurements of time and simultaneity will differ from those of co-moving observers. They will define their own slices of space-time, their own versions of now, which do not align perfectly with cosmic time. Similarly, in regions where gravity is strong, such as near massive objects, proper time deviates from cosmic time. Clocks in those regions tick at different rates, even if they are otherwise at rest with respect to the expansion. So cosmic time is not universal in the absolute sense. It is a preferred coordinate system that works well for describing the large-scale structure of the universe, but it does not eliminate the relativity of time. It does not force all observers to agree on a single present moment. Instead, it provides a useful approximation, a way of organizing events across the universe in a consistent manner, as long as you are willing to adopt the perspective of co-moving observers. This raises an interesting point. Even though relativity tells us that there is no fundamental universal now, the structure of our particular universe allows for something that behaves similarly under certain conditions. It is not built into the laws themselves, but it emerges from the way matter and energy are distributed on large scales. So in a sense, the universe offers a compromise. At the deepest level, there is no preferred present. Time is local, dependent on motion and gravity, and observers can disagree about simultaneity. But at the larger scales, where the universe appears smooth and uniform, it becomes possible to define a common timeline that many observers can share, at least approximately. This timeline does not have the same status as Newton's absolute time. It is not fundamental, and it does not apply in all situations. But it is useful, and it reflects a real feature of the universe's structure. And importantly, even this cosmic clock does not fully restore the intuitive idea of now, because the moment you step away from the idealized comoving frame, the familiar issues return. Different observers define different presents, proper time varies, simultaneity remains relative, so the search for a universal clock leads to a partial answer. Yes, there is a way to define a shared time coordinate for the universe as a whole, but no, it does not provide a universal present that applies to all observers in all situations. Instead, it sits alongside the other concepts we have developed: proper time, spacetime, relativity, as one more way of describing the structure of time without reintroducing the idea of a single global now. Look again at the expanding universe, but this time without immediately assuming that expansion gives us back something like a shared present. It is tempting to think that because everything is stretching outward in a uniform way, there must be a universal moment tied to that expansion, a kind of synchronized now, defined by the age of the universe itself. At first, this seems reasonable. If galaxies are moving apart everywhere, and if we can trace that motion backward to a much denser early state, then it feels natural to imagine that there is a cosmic clock ticking from that beginning. Each moment would correspond to a specific stage in the expansion, and everything in the universe would share that stage together. This is where the idea of cosmic now begins to take shape. You might picture it like this. The universe starts in a hot, dense state, often associated with what we call the Big Bang. As time progresses, space expands, temperatures drop, structures form and galaxies emerge. At any given cosmic time, the universe has a particular size, a particular average temperature, and a particular level of structure. So it feels as though you could say, right now, the universe is at this stage, and that statement would apply everywhere. But that intuition hides several assumptions. The first assumption is that there is a unique way to define the same moment across all of space. The second is that the expansion itself provides a preferred reference frame that all observers must agree on. The third is that local variations like motion and gravity do not significantly disrupt this global picture. Each of these assumptions works reasonably well under certain conditions, but none of them is fundamental in the same way that relativity is. To see where the complications arise, start with the observers who define cosmic time. These observers are not arbitrary. They are specifically those who are at rest with respect to the large-scale expansion of the universe. They are not moving relative to the average distribution of matter. In a sense, they are going with the flow of the expanding space-time. For these observers, the universe looks uniform in all directions. One of the clearest pieces of evidence for this comes from the cosmic microwave background, the faint glow of radiation left over from an early stage of the universe. When measured by observers who are at rest with respect to the expansion, this radiation appears almost perfectly uniform in all directions. If an observer is moving relative to this cosmic rest frame, the radiation appears slightly warmer in the direction of motion and slightly cooler in the opposite direction. This provides a way to define what it means to be at rest with respect to the universe as a whole. So in that sense, there is a preferred frame in cosmology. Observers who see the cosmic microwave background as isotropic, the same in all directions, can define a common time coordinate. That coordinate is cosmic time, and it corresponds to the age of the universe as measured along their world lines. This seems to bring us closer to a universal now. If all co-moving observers agree on the age of the universe, then perhaps they also agree on what is happening right now across space. But the key word here is co-moving. Not all observers are co-moving. Many objects in the universe have motions relative to the cosmic rest frame. Galaxies rotate, clusters interact, stars orbit, and local gravitational effects introduce variations that break the ideal symmetry. Even you, sitting on Earth, are not perfectly at rest with respect to the expansion. The Earth orbits the Sun orbits the centre of the Milky Way, and the Milky Way itself moves relative to other galaxies. All of these motions mean that your local frame of reference is slightly different from the ideal co-moving frame. These differences are usually small compared to the overall expansion, but they are not zero. And because of that, your definition of simultaneity, your slicing of space-time into moments, does not perfectly align with the cosmic one. So even within the expanding universe, different observers can define different nows. The cosmic now is tied to a specific choice of reference frame, one that is useful and well motivated but not mandatory. This is the first limitation. The second limitation comes from gravity. The large-scale structure of the universe may be uniform, but locally, matter is not evenly distributed. There are galaxies, clusters, voids, and regions of varying density. These structures create gravitational fields that affect the rate at which time passes. Clocks in stronger gravitational fields tick more slowly than those in weaker fields. So even if two observers are co-moving with the expansion, if they are located in regions with different gravitational environments, their proper times will not match exactly. This introduces small but real differences in how time is experienced across the universe. So the idea of a perfectly synchronized cosmic clock begins to soften. It works as an approximation, especially when averaged over large scales, but it does not hold exactly at every point. Now consider a deeper issue. Even if you adopt cosmic time as your preferred coordinate, you still need to define what events belong to the same moment. That means choosing a slice of space-time where the cosmic time coordinate is constant. This slice represents the universe at a particular age. For co-moving observers, this slicing makes sense. It aligns with their world lines and provides a consistent way to describe the universe's evolution. But for observers in motion relative to this frame, those slices are tilted. Their definition of simultaneity does not match the cosmic one. Events that lie on a constant cosmic time slice may not be simultaneous in their frame, so the cosmic now is not invariant. It depends on the choice of reference frame, just like any other definition of simultaneity in relativity. This brings us back to the central theme. The expanding universe does provide a natural way to define a global time coordinate. It allows us to talk about the age of the universe, to describe its evolution, and to compare different stages of its history, but it does not restore a universal now in the fundamental sense. It gives us a convenient and physically meaningful way to organize events, but that organization is still frame-dependent. Different observers can still disagree about which events are happening at the same time, even in an expanding universe. So the idea of a cosmic now is both useful and limited. It is useful because it reflects the large-scale symmetry of the universe and provides a shared reference for many observers. It is limited because it does not override the principles of relativity. Time remains local. Proper time remains tied to world lines. Simultaneity remains relative. The universe does not enforce a single present moment that all observers must agree on. Instead, it offers a structure where certain choices of now are more natural than others, especially when looking at the universe as a whole, and that subtle distinction matters. Because it shows that even when the universe appears to offer a shared clock, that clock is not fundamental in the way our intuition might expect. It is a feature of the universe's large-scale behaviour, not a rule built into the fabric of space-time itself. So the expanding universe brings us close to the idea of a universal now, but never quite all the way there. Shift your attention away from the large-scale structure of the universe and move instead into the smallest scales we can meaningfully describe. Not galaxies, not space-time curvature, but particles, fields, and probabilities. Because when physics steps into this domain, the role of time changes again, and in a way that feels almost disconnected from everything we've built so far. Up to this point, time has been flexible, but still present. Relativity showed that time depends on motion and gravity. It showed that there is no universal now, and that each observer carries their own proper time. But time itself still exists as part of the structure. It is woven into space-time, even if it behaves differently for different observers. Quantum mechanics approaches things differently. In the standard formulation of quantum mechanics, time is not treated in the same way as space. It does not become part of a geometric structure like space-time. Instead, it plays a more external role, almost like a parameter that keeps track of how systems evolve. This difference might seem subtle at first, but it has deep consequences. In quantum theory, the state of a system is described by something called a wave function. This wave function encodes the probabilities of different outcomes, the likelihood of finding a particle in a certain place, or measuring a certain value. The wave function evolves over time according to a specific equation, often written as the Schrödinger equation. What matters here is how time appears in that equation. Time is not an operator like position or momentum. It is not something you measure in the same way. It is a parameter that tells you how the system changes, but it is not itself subject to the same kind of quantum uncertainty. So in quantum mechanics, time is more like a background variable. It flows uniformly in the equations, allowing you to calculate how the system evolves from one moment to the next. This might sound familiar, almost like a return to the classical idea of time as a steady backdrop. But there is a tension here. Relativity tells us that time is not absolute, that it depends on motion and gravity, and that different observers have different measures of time. Quantum mechanics, in its standard form, assumes a single time parameter that applies to the entire system. These two views do not fit together neatly. This is one of the central challenges in modern physics. When you try to combine quantum mechanics with general relativity, the role of time becomes unclear. In relativity, time is part of the dynamical structure of spacetime. In quantum mechanics, it sits outside the system, guiding its evolution but not being affected by it. So the question arises, which version of time is more fundamental? Or is there a deeper description in which time is not fundamental at all? Before going that far, it helps to look at how quantum mechanics treats the idea of now. In everyday thinking, now feels like a precise moment, a boundary between past and future. But in quantum mechanics, the situation is less clear, because quantum systems are not always in definite states until they are measured. Instead, they can exist in superpositions, combinations of multiple possibilities at once. A particle can be in many positions simultaneously, or have multiple possible energies until an observation is made. So when exactly does something happen? Does it happen at a specific moment in time, or does the concept of a precise moment become blurred? This leads to what is sometimes called the measurement problem. When you measure a quantum system, the wave function appears to collapse from a range of possibilities into a single outcome, but the theory itself does not specify exactly when or how this collapse occurs. Time is present in the equations, but the transition from possibility to actuality is not tied to a clearly defined instant in the same way classical events are. So even the idea of an event happening at a precise now becomes less straightforward. In some interpretations of quantum mechanics, such as the many worlds interpretation, the wave function never collapses at all. Instead, all possible outcomes continue to exist in a branching structure of realities. In that picture, there is no single moment where one outcome becomes real and others disappear. All outcomes exist simultaneously in a larger structure. This echoes something we saw earlier in the block universe. Instead of a single, unfolding present, you have a structure that contains many possibilities, with observers experiencing particular sequences within it. Other interpretations, like relational quantum mechanics, suggest that the properties of a system only become definite relative to an observer. This further complicates the idea of a universal now, because different observers may not agree on the state of a system at the same time. So quantum mechanics does not restore a shared present. If anything, it adds another layer of complexity. Not only do observers disagree about simultaneity due to relativity, they may also disagree about the state of a system due to quantum effects. And underlying all of this is the peculiar role of time itself. In quantum theory, time is not something that can be put into a superposition. You do not have a system that is in two times at once, in the same straightforward way that it can be in two positions. Time remains a parameter, something that orders the evolution of the wave function, but not something that behaves like other physical quantities. This creates a kind of asymmetry. Space and time are unified in relativity, but separated again in quantum mechanics. And when physicists try to build a theory of quantum gravity, a framework that unites these two pillars, this asymmetry becomes a major obstacle. Some approaches suggest that time might emerge from more fundamental timeless structures. In these ideas, the universe at its deepest level may not contain time as a basic ingredient. Instead, time could arise from relationships between more fundamental variables, appearing only at larger scales where certain patterns emerge. If that is the case, then now would not be a fundamental feature of reality at all. It would be something that emerges from the way observers interact with the world, from the way information is processed and structured, rather than something built into the underlying laws. So as we move into the quantum domain, the question shifts again. It is no longer just about whether there is a universal now, but about whether time itself, as we understand it, is a basic part of reality, or something that appears only under certain conditions. Try placing the two most successful theories in physics side by side, not as separate achievements, but as descriptions of the same universe that somehow refuse to agree on one very basic thing. On one side, you have relativity, where time is flexible, local, and woven into the geometry of spacetime itself. On the other, you have quantum theory, where time sits outside the system, acting as a steady parameter that tells everything else how to evolve. Individually, both frameworks work with extraordinary precision. Together, they create a tension that runs directly through the concept of time. This tension is what physicists refer to as the problem of time in quantum gravity. It is not a single equation that fails or a specific experiment that does not match predictions. It is something more structural. When you try to build a theory that includes both quantum mechanics and gravity, the role of time becomes unclear, almost as if the two theories are describing different aspects of reality using incompatible assumptions. To see why this happens, it helps to restate the contrast in a slightly different way. In general relativity, developed by Albert Einstein, time is dynamic. It is not a fixed background. It is part of space-time, and space-time itself can bend, stretch, and evolve in response to matter and energy. The geometry is not given in advance. It is determined by the distribution of mass and energy in the universe. So in relativity, time is something that can change. Clocks tick at different rates depending on motion and gravity. There is no universal timeline. Everything is local, tied to world lines and the curvature of space-time. Now compare that to quantum mechanics. In standard quantum theory, time is not dynamic in that way. It does not bend or respond. It is assumed to exist as a fixed parameter. The equations describe how a system changes with respect to time, but time itself is not part of the system being described. It is as if time is outside the quantum world, providing a reference that everything else depends on. This works well when gravity is weak, and space-time can be treated as approximately fixed. But when you try to include gravity at the quantum level, this separation breaks down, because in a theory of quantum gravity, space-time itself must be subject to quantum principles. It cannot remain a fixed background. it must be able to exist in different states, perhaps even in superpositions, just like other physical quantities. And once spacetime becomes quantum, time cannot remain external. It must be treated as part of the system. This is where the problem begins. If time is part of the system, then what does it mean for the system to evolve in time? In ordinary quantum mechanics, you describe the state of a system at one time and then calculate how it changes at later times. But if time itself is not fixed, if it is part of the quantum system, then there is no external parameter to define that evolution. So the usual idea of time evolution becomes difficult to define. One of the most striking expressions of this issue appears in an equation known as the Wheeler-DeWitt equation, which arises in certain approaches to quantum gravity. Without going into the technical details, the important point is this. In that equation, there is no explicit time variable. The equation describes a state of the universe as a whole, but it does not include a parameter that represents time flowing or progressing. In a sense, it describes a timeless state. This is sometimes referred to as the frozen formalism. From the perspective of the equation, nothing changes. There is no built-in notion of before and after. The universe is described as a whole, rather than as something evolving through time. At first, this seems completely at odds with experience. You clearly perceive change, you remember the past, you anticipate the future, and you experience a continuous flow of time. How can a fundamental theory describe a universe where time does not appear, when your entire experience is structured around it? This is the heart of the problem. Time appears in our experience, and it appears in many practical calculations, but it may not appear in the most fundamental description of the universe. So the question becomes, if time is not fundamental, how does it emerge? One approach to this question is to consider time as something that arises from correlations between different parts of a system. Instead of having a single external time parameter, you can describe one part of the system changing relative to another. For example, you might use the position of a clock-like subsystem to define a notion of time, and then describe how other parts of the system change with respect to that. In this view, time is relational. It is not something that exists independently. It is something that emerges from the relationships between different variables. This idea fits naturally with some interpretations of quantum mechanics, where properties are defined relative to observers or interactions. It also aligns, in a subtle way, with relativity, where time is already local and tied to world lines rather than being universal. But even with this approach, the sense of a flowing now does not reappear in a fundamental way. At best, you recover an effective notion of time, something that works at larger scales and for specific observers, but not something built into the deepest level of reality. So at the level of quantum gravity, the situation becomes even more unusual than before. Relativity removed the universal present. Quantum mechanics blurred the definition of events and introduced uncertainty. Quantum gravity suggests that time itself may not be a basic ingredient at all. Instead of asking whether there is a universal now, the question begins to shift towards something more radical. Is time something the universe has, or something that appears only when certain conditions are met? And if time is emergent, then now would be emergent as well. It would not exist as a fundamental slice of reality. It would arise from the way observers, systems, and interactions are organized. This perspective does not eliminate time from your experience. You still live along a world line. You still measure proper time. You still experience sequences of events, but it places that experience within a larger framework, where the underlying structure may not include time in the way we intuitively expect. So the problem of time is not just a technical issue in theoretical physics, it is a reflection of how deeply our understanding of time depends on the frameworks we use. When those frameworks are combined, the concept of time itself becomes uncertain, not in the sense of being random, but in the sense of being something that may not exist in the same way at all levels of description. And once you reach that point, the original question about now begins to look very different. Pause for a moment before answering too quickly, because this is where everything we've built starts to circle back on itself. The question sounds simple, almost casual, but by now it carries the weight of everything that came before it. Does now actually exist? Not in the everyday sense, not in the way you casually refer to the present moment, but in the sense of something fundamental, something built into the structure of the universe itself, something that exists independently of observers, motion, gravity, or interpretation. Because if such a now exists, it would have to survive everything we've explored. It would need to remain meaningful despite relativity removing simultaneity, despite proper time becoming personal, despite gravity stretching time unevenly, despite quantum theory blurring events, and despite quantum gravity suggesting that time itself might not be fundamental. So instead of answering immediately, it helps to narrow the question. What kind of now are we talking about? There are really two possibilities. One is a universal now, a single moment that spans the entire universe, connecting all events into one shared present. The other is a local now, something tied to an observer, something that exists only along a specific path through space-time. The first idea is the one that feels intuitive. It is the sense that there is a global present, that somewhere out there, across all distances, there is a single moment that everything shares. It is the idea that when you say right now, you're referring to something that applies everywhere. But by this point, that idea has been steadily dismantled. Relativity shows that simultaneity depends on motion. Two observers moving differently will disagree about which events are happening at the same time. There is no way to define a single slice of space-time that all observers must accept. Gravity adds another layer, causing time to pass at different rates depending on position. Even observers who are not moving relative to each other can experience different amounts of time. Black holes push this further, creating situations where different observers cannot even agree on whether certain events have happened yet. Cosmology offers a partial reconstruction through cosmic time, but only within a specific reference frame, not as a fundamental feature. Quantum mechanics complicates the notion of events themselves, and quantum gravity suggests that time may not exist in a fundamental way at all. So if you are asking whether a universal now exists, the answer from modern physics is clear. No. There is no evidence for a single, observer-independent present moment that spans the universe. There is no preferred slice of space-time that defines what is happening right now, everywhere. That idea, as natural as it feels, does not survive contact with the structure of reality as described by our best theories. But that is not the end of the question, because the second idea of now, the local one, has not been removed. At every point along your world line, there is an event that corresponds to your current state. That event is well defined. It is not ambiguous. It does not depend on distant observers or arbitrary choices of reference frame. It is simply where you are in space-time. That is your now. It is not a slice across the universe. It is a point. Everything you experience is tied to that point. Your thoughts, your perceptions, your awareness, all occur at that event. The rest of the universe is connected to it through signals, delays, and causal relationships, but it is not part of a shared present in any universal sense. So in that way, now does exist, but only locally. It exists as part of your experience, as part of the path you take through space-time. It is not something that stretches across the universe. It is something that moves with you. This leads to an important distinction. The universe does not contain a universal present, but it does contain observers who experience a present. And that experience is consistent with the structure of space-time. Your now is simply the point where your world line intersects the sequence of events you're experiencing. It advances as you move forward along that path, giving the impression of a flowing present. But that flow is not something happening to the universe as a whole. It is something happening within your experience. This becomes even more interesting when you consider the possibility that time itself may be emergent. If time is not fundamental, if it arises from deeper relationships between physical systems, then now would also be emergent. It would not exist at the most basic level of reality. It would appear only at higher levels, where observers, memory and information processing come into play. In that case, now is not something the universe has independently. It is something that appears when certain conditions are met. Conditions like having a system that can store information about past states, compare it to current states, and form expectations about future states. In other words, conditions like having an observer. So the existence of now may depend on the existence of systems capable of experiencing it. Without observers, there would still be events, still be spacetime, still be relationships between those events. But there might not be anything that corresponds to a present moment in the way we understand it. That idea can feel unsettling at first, because it suggests that something as immediate as now is not a fundamental part of reality. But it also provides a way to reconcile the gap between physics and experience. Physics describes a structure without a universal present. Experience provides a sense of a moving present. The two are not in conflict once you recognize that they are describing different levels of the same system. So when you ask, does now exist? The answer depends on what you mean. If you mean a universal shared moment that spans the entire universe, then no, it does not exist. If you mean the local, immediate point of experience along a world line, then yes, it does exist. And if you look deeper, at the level where time itself may not be fundamental, then now becomes something that emerges, something that appears when the right conditions are in place, rather than something that is built into the fabric of reality from the beginning. So the question does not have a single answer. It has layers. At one level, now disappears. At another, it remains. An understanding that distinction is what allows the entire picture to hold together without contradiction, even if it no longer matches the simple intuition we started with. After moving through all of this, from the everyday sense of a shared present to the deepest questions about whether time itself even exists, it becomes possible to return to something much closer, something that has been present the entire time but perhaps unnoticed. Not the universe as a whole, not distant observers, not abstract equations, but your position within all of it. Because even though physics removes the idea of a universal now, it does not remove your experience of being somewhere in time. That experience remains steady. Right now, wherever you are, whatever you're doing, you're located at a specific event in spacetime. Not a vague moment, not a philosophical concept, but a precise point defined by where you are and when you are. That point is part of your world line, the path that traces your existence through the universe, and from that point everything else unfolds. What you remember belongs to earlier points along that path. What you anticipate lies further along it. Signals from distant places arrive and become part of your experience, each carrying information from events that happened elsewhere, at different times, under different conditions. So even though there is no single now that stretches across the universe, there is always a here and now for you. It is local, it is specific, and it is consistent with everything physics describes. This is where the question begins to soften. Instead of asking whether now exists as a universal feature, it becomes more meaningful to ask how your experience of now fits into the structure we have explored. And the answer is that it fits naturally. Your now is simply your position along your world line. It is the event you are currently experiencing. It does not need to extend across space. It does not need to align with distant events. It only needs to be consistent with the path you're following through space-time. Everything else, all the complexity we discussed, arises when you try to connect your now with someone else's, especially across large distances or under different conditions. That is where relativity enters. That is where simultaneity breaks down. That is where time becomes personal. But none of that removes the reality of your own present moment. It simply places it within a larger framework. You can think of it this way. The universe does not provide a single shared stage where everything happens at once. Instead, it provides a vast structure of events and relationships, and within that structure, each observer traces their own path. Along that path, there is always a current point, always a present event. So while there is no universal now, there are countless local nows, each tied to an observer, each moving forward along a world line. And those local presents are enough to build everything you experience. They allow for memory, for anticipation, for decision-making, for awareness. They allow you to construct a sense of continuity, even in a universe that does not enforce a global timeline. This leads to a quiet realization. The absence of a universal present does not make the universe less real or less structured. It simply means that the structure is more subtle than our intuition first suggests. Instead of a single flow of time carrying everything together, there is a network of paths, each with its own measure of time, each with its own sequence of events. And within that network, your experience unfolds. You're not outside of time, and you're not disconnected from it. You're embedded in it, following a specific trajectory, experiencing a specific sequence of events, all consistent with the laws that govern space-time. Even if those laws do not include a universal now, they still include everything needed for your experience of the present to exist. So the original question, is there really a now in the universe, turns out to have a layered answer. There is no single shared present that spans everything, but there is always a present for you. And that distinction is what allows both physics and experience to coexist without contradiction. So as you sit here, listening, thinking, or perhaps just letting your mind drift, you are at one point along a path that extends through space-time. That point is your now. It does not need to match anyone else's perfectly. It does not need to align with distant galaxies or observers moving at different speeds. It simply is where you are. And from there, everything else, past, future, memory, expectation, all connects through the structure we've been exploring. Which means that even in a universe without a universal present, your place in time remains clear. And as your world line continues, carrying you forward through space-time, that quiet, local sense of now moves with you, not as something imposed by the universe, but as something that emerges naturally from your place within it.